Have you ever noticed that as you lie still, at the end of the day, the universe itself seems to slow its pace? Your breath slows, your thoughts drift, and yet all around you immense forces are quietly at work, shaping worlds, stars, and entire galaxies without sound or urgency. Tonight, let us begin with a simple question. Why does the universe, across every scale we can observe, seem to favor curves over corners, spheres over edges, roundness over sharpness? From the smallest drop of water to the largest planet hanging in the dark, the same shape keeps returning, as if nature itself is gently insisting on it. This is not coincidence, and it is not decoration. It is the outcome of a deep and ancient conversation between forces that never sleep. As we ease into this story, let us step beyond appearances and listen carefully, because beneath that quiet preference for roundness lies a struggle that decides the form of every world. And so we arrive at the first part of our journey. Part 1. What struggle decides the form of a planet? Somewhere in the stillness of space, an unseen conflict is forever underway, a conflict that determines what every world will ultimately become. It is not a battle of destruction, but one of balance, between two forces older than light itself, gravity and rotation. Gravity is the universe's most enduring touch. It draws dust, stone, and gas inward toward a single center, endlessly pulling, endlessly seeking balance. Rotation, by contrast, is its restless counterpart, motion that refuses to remain still. It tugs matter outward, stretching it, distributing energy across space. From this timeless negotiation emerges the shape of every planet, star, and galaxy. When a world first begins to take form, there is no solid surface. Only a swirling cloud, a collapsing and rotating sphere of gas and debris moving within the turbulence of a newborn star system. According to planetary formation models from NASA, these structures, known as protoplanetary disks, rotate because the original nebula that gave birth to them was already spinning. The conservation of angular momentum ensures that as a cloud contracts under its own gravity, it must rotate more rapidly, much like a figure skater drawing their arms inward. As the cloud grows denser, gravity steadily gains dominance. It begins to pull matter inward equally from every direction. This is the true origin of roundness. Gravity acts isotropically. It has no preference for up or down, left or right. Its pull is identical in all directions. And this is why the sphere is nature's default form. As astrophysicist Neil deGrasse Tyson once observed, gravity is the great sculptor of the universe, patiently smoothing everything over time. Yet this sculpting is never straightforward, because from the very moment a world forms, it also begins to spin. And rotation resists perfection. Earth, for instance, completes a full rotation once every 23 hours, 56 minutes and 4 seconds. That motion produces a centrifugal effect strongest at the equator. As a result, our planet is not a perfect sphere. It is an oblate spheroid, subtly flattened at the poles and gently swollen at the equator. The difference between Earth's equatorial and polar diameters is approximately 43 kilometers, as confirmed by measurements from NASA's Earth Observatory. Every planet we have studied tells the same story. Jupiter, the fastest rotating planet in our solar system, completes a full spin in less than 10 hours. Its rapid rotation creates a pronounced equatorial bulge. Its diameter at the equator exceeds the distance from pole to pole by more than 9,000 kilometers. Saturn carries this effect even further. Composed largely of hydrogen and helium, it spins so quickly and has such low density that its poles appear visibly compressed, a world stretched by the very motion that sustains it. This pattern echoes throughout the universe. Stars also flatten slightly as they rotate. The star Achernar, located 139 light-years away in the constellation Eridanus, spins at such extraordinary speed that it becomes dramatically elongated. Its equatorial diameter is roughly 50% greater than its polar diameter, as observed by the Very Large Telescope in Chile. Even entire galaxies follow the same principle. The Milky Way's familiar spiral form a vast, flattened disk of stars and gas is simply gravity and rotation arriving at a long-term truce. So when everything from droplets of water to galaxies displays this same behavior, the conclusion is unavoidable. This dance between gravity and rotation is universal. According to the European Space Agency's Gaia mission, stars are born within immense molecular clouds that slowly collapse into spherical cores. Yet the conservation of angular momentum stretches those cores into disks. From those disks emerge planets. From planets come moons. And from moons, the quiet elegance of roundness repeats again and again across the night sky. But gravity does more than shape the surface. It works relentlessly toward the center. Deep beneath Earth's crust, pressure increases to nearly 3.6 million times the air pressure at the surface. That unimaginable weight holds every layer tightly together, stable and nearly spherical. The same process unfolds within Jupiter, where pressures exceed 100 million atmospheres, compressing gas into strange and exotic forms of metallic hydrogen. Out there, far beyond the familiar canopy of our sky, gravity still insists on order. Researchers have often put it plainly: the universe has little tolerance for imbalance. Whenever energy piles up in one place, gravity quietly sets about restoring harmony. Over immense spans of time, this is why chaotic forms, jagged asteroids, misshapen moons, gradually surrender their rough edges and become almost perfectly spherical once they grow massive enough. There is a tipping point for this transformation known as hydrostatic equilibrium. It usually appears when a body grows larger than roughly 600 kilometers across. Beyond that size, its own gravity overwhelms the strength of the material holding it, rigid, drawing everything inward until roundness emerges. That is why Ceres in the asteroid belt is smooth and spherical, while smaller objects like Eros or Phobos remain irregular and scarred. Nothing mystical is happening here. It is physics etched directly into matter. Size changes the outcome. Grow large and gravity dominates. Stay small and internal structure holds its ground. Every world tells the story of this slow, silent contest. And the rule does not stop with planets or moons. It extends all the way to the most extreme objects we know. The largest black holes, where gravity reigns without rival, represent the ultimate expression of this process. Within Einstein's general theory of relativity, a black hole that does not rotate is described by a solution that predicts a flawless spherical curvature of space-time. Introduce rotation and the picture changes. Space twists, bulges and drags along with the spin. Once again, two influences bargain with each other. Gravity attempts to collapse everything into a single point, while rotation stretches space into motion and flow. It is not the ingredients of a world that define it, but the way those ingredients are arranged. The same idea applies across the cosmos. Dust, rock, gas, even hydrogen matter less than the patient way they yield to gravity and respond to the restless pulse of spin. And yet, as deeply as we explore, nature continues to surprise us with exceptions. Some neutron stars spin hundreds of times each second, rotating so rapidly they verge on tearing themselves apart. The fastest known pulsar turns more than 700 times every second. At its equator, matter races along at over 100,000 kilometers per second, close to a third of the speed of light. Under such conditions, matter distorts space, stretches, and time itself slows. The balance remains, but it quivers at the very limits of physical law. Wherever we look, the same quiet message returns. Nothing is truly at rest, yet everything seeks symmetry. A tiny droplet drifting inside the International Space Station pulls itself into a perfect sphere. A young planet shapes itself amid violent collisions and swirling debris. A black hole bends the very geometry of space into a form that challenges our language. This is no accident. It is one of the most persistent truths we know. From the graceful arcs of Saturn's rings to the gentle curve of Earth's horizon, the universe speaks in geometry, the language of balance. As scientists chart the cosmos with instruments like the James Webb Space Telescope, they continue to find symmetry emerging where chaos once seemed to dominate. Roundness appears to be the universe's favoured response to disorder. Yet beneath that calm surface, the struggle never ceases. Gravity pulls inward, offering unity. Spin presses outward, demanding freedom. Every world we observe, including our own, is a paused instant in that endless negotiation. Within this tension lies the reason planets assemble, galaxies flatten, and stars ignite. The shapes we take for granted are not decoration. They are evidence of how deeply connected every atom, every movement, every force truly is. The next time you watch the moon rise flawlessly curved and utterly silent, remember that its shape was earned through billions of years of compromise between unseen giants. And as we move deeper into this story, another question begins to surface in the darkness. When gravity folds space back upon itself, what shape does it choose? At the center of our galaxy resides something so massive and dense that even light, the swiftest traveler in the universe, cannot escape its grip. And yet, despite its violence, it is thought to be the most perfect sphere nature can produce: the black hole. Astronomers know it as Sagittarius A, a supermassive object, nearly 4.3 million times the mass of our Sun, resting some 26,000 light-years away in the direction of Sagittarius. To human eyes, it remains unseen. But in 2022, the Event Horizon Telescope delivered something extraordinary: the first direct image of a black hole's shadow, a faint, luminous ring encircling a profound darkness. It was not simply a picture, it was geometry made visible, space and time themselves bent into an almost flawless symmetry. In Einstein's framework, a black hole without rotation is known as a Schwarzschild black hole. Such an object is described by a single quantity, its mass forming a perfectly spherical distortion of space-time around a central point called a singularity. Surrounding that singularity lies the event horizon, the ultimate boundary from which nothing, not even light, can escape. Its scale is given by a remarkably simple expression: r equals 2 times the gravitational constant multiplied by mass divided by the square of the speed of light. For Sagittarius A, that radius measures roughly 12 million kilometers, about 1/10 of the distance between the Sun and Mercury. Inside this boundary space, and time exchange roles and gravity reaches its most extreme expression. Yet no black hole in the real universe is ever truly motionless. Every collapsing star carries rotation with it. When such a star dies, that spin does not disappear. It is compressed and intensified. The outcome is a rotating black hole, its shape stretched and distorted by motion. Rather than a static, perfectly symmetrical horizon, it becomes an oblate spheroid, flattened at the poles and swollen at the equator, a cosmic parallel to the shapes of Earth or Saturn. But when rotation approaches its limits, space-time itself behaves like an elastic fabric, and the equations suggest something even more remarkable. The horizon can contort toward a toroidal form, a gravitational donut. Matter and light no longer fall straight inward, but circulate within a zone known as the ergosphere, where space itself is dragged along by rotation. This phenomenon, called frame dragging, was experimentally verified in 2011, when a space-based experiment detected the subtle twisting of space-time caused by Earth's own spin. Near a black hole, that same effect becomes overwhelmingly strong, capable of winding light into spirals and accelerating particles to velocities approaching that of light. Observations from the Event Horizon Telescope indicate that the black hole at the center of the galaxy M87, first imaged in 2019, exhibits precisely this kind of rotation. Its colossal jets, vast streams of plasma stretching some 5,000 light-years into space, are best explained by a rapidly spinning black hole drawing energy from its own rotation. This mechanism is now regarded as a primary way in which galaxies generate and sustain their immense magnetic structures. And yet, for all that violence and motion, the visible outline of the black hole, the shadow itself, remains hauntingly circular. Even when warped by rotation, relativity bends light so effectively that the resulting image appears almost perfectly round to a distant observer. Measurements showed deviations of no more than 10% from a perfect sphere, reinforcing the accuracy of Einstein's predictions. The closer scientists look, the more unsettling this precision becomes. If the mathematics is stripped away, what remains is an object defined by profound simplicity. Black holes possess no distinguishing features, no surface detail, no memory of the chaos that formed them, only mass, charge, and spin. Everything else, the chemistry, the structure, the history of the parent star, vanishes without a trace. That silence can be detected. In 2015, observatories on Earth recorded gravitational waves ripples in space-time, produced by two black holes, merging each around 30 times the mass of the Sunday. The signal carried the unmistakable imprint of symmetry as the pair collapsed into a single larger sphere. It was described as the most violent event ever observed, and yet its underlying geometry was strikingly simple, almost serene. Rotation, however, always complicates serenity. As spin increases, the horizon flattens further. If a black hole were to rotate beyond the limits allowed by relativity, the equations would fail, revealing what is known as a naked singularity, a core laid bare. No such object has ever been seen. Nature appears to conceal its most extreme states behind the curtain of the event horizon. Even now, the James Webb Space Telescope observes galaxies in which central black holes shape the birth of stars across distances of thousands of light years. The rotation and magnetic fields generated by these concealed titans sculpt entire cosmic systems. The very geometry that confines light also governs the long arc of cosmic evolution, determining how gas cools, how stars are born, and how matter is endlessly recycled through the interstellar medium. In 2024, fresh results from the Chandra X-ray Observatory revealed that some supermassive black holes rotate at almost 99% of the theoretical maximum, an astonishing state of energy capable of driving radiation across the entire electromagnetic spectrum, from radio waves to X-rays. And yet, even under such extremes, the event horizon holds its form. It does not tear apart. It does not cave in on itself. Instead, it swells gently at the equator, maintaining equilibrium, like a dancer caught in a perfect turn. Here lies the quiet paradox of black hole roundness. As spin increases, the internal structure of space-time grows ever more distorted, and still the visible outline stubbornly preserves its circular grace. To our eyes, these objects remain the most symmetrical entities we have ever encountered. But within that circle, there is no surface, no ground to stand on. Matter is crushed beyond atoms, beyond particles, beyond any familiar description. Theory tells us that at the core, density becomes infinite. Yet infinity is not a quantity we can handle. It is a signal, a marker, that our mathematical language fails beyond this point. Even Einstein's equations, so elegant and so precise, fall silent there. A black hole marks the place where the map ends and the unknown begins. And in that unknown may lie the route to quantum gravity, the long-sought union between general relativity and quantum mechanics, the two most successful yet incompatible descriptions of reality we possess. Perhaps the clue is written in the shape itself. In physics, symmetry is never ornamental. It is structural, the expression of conservation laws. The near-perfect spherical form of a non-rotating black hole reflects one of the deepest properties of space-time, isotropy, the idea that the laws of physics are the same in every direction. That is why across billions of light years gravity pulls evenly, and why roundness appears again and again at every scale of nature. But the moment motion enters the picture, symmetry begins to bend. A spinning black hole drags space, and space in turn drags time. Together they twist the universe into a graceful spiral of relativity. This is not disorder. It is the most refined distortion possible. Even the universe itself cannot resist motion. It expands, it curves, and on the largest scales, it may even carry its own slow rotation. Physicists often describe black holes as laboratories of gravity. They are not merely regions of darkness. They are experiments conducted by nature revealing what happens when mass, energy, and geometry are pushed to their absolute limits. Every photon that skims the edge of the horizon becomes a messenger carrying information about the deepest workings of space-time. To study a black hole is to contemplate the cleanest shape in existence, not because it is smooth or luminous, but because it is final. There are no imperfections, no remnants of its birth, only curvature and gravity locked in perfect agreement. It is the most motionless object in the universe, born from the most violent events imaginable. And yet that stillness is deceptive. Spin ensures that nothing is ever perfectly round. Even the black hole, that ultimate monument to gravity, bears a subtle flaw, a bulge created by motion and frozen into its frame. Nature, it seems, never truly comes to rest. The universe owes us no obligation of clarity, yet it leaves behind patterns, quiet signatures that echo from atoms to galaxies. The roundness of black holes is one such pattern, a reminder that the same laws shaping our everyday world also govern the stars. And while we cannot yet peer inside these dark spheres, each improvement in how we measure their shadows reveals more about how space itself behaves. Every bent photon, every traced orbit, every recorded ripple of gravity speaks a single language geometry. So when you see the glowing ring captured by the Event Horizon Telescope, remember that you are not looking at an object in space. You are seeing space-time itself curved with exquisite precision around nothing at all. The universe reduced to its purest mathematical expression. And if even black holes, the most extreme structures known, are ruled by symmetry, what of the vast galaxies that spin for billions of years, flattening into elegant spirals rather than perfect spheres, as though gravity and motion were painting together on a cosmic canvas? Part 3. Why do galaxies take on a flattened form? If gravity so clearly favors roundness, if it tirelessly pulls matter towards spheres, why did the Milky Way fail to remain one? Why did countless stars, immense clouds of gas, and vast quantities of unseen dark matter settle into a luminous disk so slender that, scaled to a dinner plate, our sun would be nothing more than a grain of dust at the edge? At first sight, it feels paradoxical. Every planet, every star, every small clump of matter shaped by gravity naturally becomes round, the most efficient and stable configuration. And yet galaxies, the largest coherent structures in the universe, stretch themselves into spirals, bars, and elongated forms, drifting through space like colossal whirlpools. To grasp why this happens, we must look not at stars, but at what existed before them, immense clouds of gas. About 13.6 billion years ago, the earliest galaxies began life as enormous clouds of hydrogen and helium, collapsing under their own gravity. Within those clouds, even the faintest initial twist, barely more than a whisper of rotation, was enough to determine their future. As cosmological simulations show, when a cloud collapses, the conservation of angular momentum demands that its rotation speeds up. It is the same effect you see when a skater draws in their arms and spins faster. As the cloud shrinks, its rotation accelerates dramatically. Over millions of years, this collapse reshapes the cloud into a rotating disk, with gas and dust settling into a shared plane, forming what astronomers call a galactic disk. The rotation of the Milky Way is extraordinary. Our galaxy, containing somewhere between 100 and 400 billion stars, along with gas, dust, and dark matter, completes a single rotation roughly every 230 million years. The last time it did so, dinosaurs were only just beginning to roam the Earth. Each star moves at an average speed of about 220 kilometers per second, bound by gravity, but carried forward by a spin inherited from the universe's earliest moments. Gravity alone does not explain this flattening. Inside a rotating cloud, particles of gas and dust move chaotically, colliding again and again. These collisions tend to cancel motion above and below the plane of rotation, while leaving sideways motion largely intact. The result is matter being forced into an ever thinner layer until a disk naturally emerges. This is why galaxies, much like planetary systems, form in a single plane, the path of least resistance. Observations from the James Webb Space Telescope have revealed disk-shaped galaxies existing just 600 million years after the Big Bang. Even at that early stage, long before the Milky Way formed, flattening was already underway. These observations suggest that the tendency toward rotation and disks appeared almost as soon as gravity began organizing matter on large scales. Gravity pulls inward, always seeking roundness, but rotation insists on spreading matter out. The universe does not choose between them. It allows both to coexist. Scene edge on the Milky Way would appear as a razor-thin line of light, about 1,000 light-years thick and nearly 1,000 light-years across. Most of the galaxy's visible material resides in this thin plane. Beyond it lies a vast, invisible halo of dark matter, roughly spherical in shape. That halo is evidence that roundness never truly vanished. It simply became hidden beneath the glowing disk. Without this halo, the galaxy could not remain intact. As stars orbit the galactic center, their speeds stay almost constant, regardless of distance, something ordinary gravity cannot explain. Measurements from the Gaia mission show that the dark matter halo provides most of the gravitational pull, shaping the galaxy's rotation and preventing it from flying apart. Within the disk itself, structure emerges through density waves, subtle ripples of gravity that compress gas and ignite star formation. These waves give rise to the familiar spiral arms seen in images from space telescopes. The arms are not fixed structures, but moving patterns, more like traffic jams than solid objects, with stars drifting in and out over time. At the heart of it all lies the galactic bulge, a dense, roughly spherical region about 1,000 light-years across. At its center sits Sagittarius, A*, the supermassive black hole anchoring the core. Here gravity dominates, motion slows, matter piles inward, and roundness reasserts itself. Farther out rotation becomes the ruling influence, flattening the galaxy into a plane. It is a delicate compromise. Near the center, gravity shapes spheres. Farther away, rotation sculpts disks. The outcome is a layered structure, a spherical core, a thin rotating disk, and a surrounding halo, all governed by the same laws under different conditions. This pattern is repeated across the universe. Spiral galaxies such as Andromeda, Triangulum, and NGC 1300 share the same basic design. Thin rotating disks encircle dense central bulges. Even the smallest dwarf galaxies observed by Webb show hints of rotational flattening. So why are galaxies flat? Because gravity and motion are always at work. One draws matter inward, the other keeps it spinning, and the balance between them produces a disk, the most stable shape for a rotating system. This is not disorder, it is structure born from motion. Space telescopes have long classified galaxies as spiral, elliptical, or irregular, but these differences arise from the same underlying physics. Elliptical galaxies with little overall rotation remain puffed up and rounded. Spiral galaxies, rich in angular momentum, are thin and elegant. The faster the spin, the flatter the form. What is remarkable is that the Milky Way is still evolving. Every stellar orbit, every drifting cloud of gas, every small galaxy, it absorbs subtly, reshapes the disk. Gaia has revealed ripples and warps at the galaxy's outer edges, scars left by past encounters with smaller galaxies. The Milky Way bends and flexes like a sheet of cosmic silk, still vibrating from ancient collisions. Beyond our galaxy, the same process continues. Andromeda, 2.5 million light-years away, is moving toward us at about 110 kilometers per second. In around 4.5 billion years, the two disks will collide and merge into a single massive elliptical galaxy, rounder, slower, and more settled. When rotation is disrupted, roundness returns. In studying galaxies, we see the universe learning its own geometry, finding equilibrium between collapse and motion. Every spiral disk is a record of that agreement, a memory of how gravity and spin learned to share control. The faint glow of the Milky Way's arms traces the rhythm of a rotation so vast we cannot sense it, even as we orbit the galactic center at 220 kilometers per second, drifting gently through the disk. The night sky appears calm, but nothing within it is truly still. What keeps galaxies flat is not the absence of gravity, but its partnership with motion. The same relationship that shaped stars and planets operates here on a scale beyond imagination. The Milky Way is neither perfectly round nor randomly formed. It is balance expressed across 1,0,0,0,0 light years. As our telescopes peer deeper into space, from Hubble to Webb, the same pattern emerges again and again. Motion spreads matter outward, gravity molds it into coherence. Even apparent chaos follows rules. And when you look up and see the arc of the Milky Way stretching across the sky, remember that this thin ribbon of light is the result of 13 billion years of cosmic negotiation, gravity's steady pull, and motion's endless spin shaping. Something delicate yet exquisitely balanced. And if rotation can flatten galaxies, what shape does the universe itself take when everything spins together? Every star and every cluster bound in motion. Is the cosmos round flat, or something stranger still beyond the reach of simple geometry? Part 4. Is the universe curved like a sphere, or does it extend as something flat and unbending? If everything began in a single violent birth, it feels intuitive to imagine the cosmos swelling outward like an enormous balloon. And yet when we turn our most sensitive instruments toward the furthest reaches of time, the story they tell is far more surprising. On the largest scales we can measure, space itself seems to be flat. In 2018, the European Space Agency's Planck mission unveiled the most precise map ever created of the cosmic microwave background, the faint ancient glow left behind by the Big Bang. This radiation, stretched into microwaves by 13.8 billion years of expansion, carries minute temperature variations. Those tiny differences are not noise. They are the imprints of the universe's earliest structure, preserved across cosmic time. When scientists studied these delicate ripples, they uncovered a remarkable result. The geometry of the universe is flat to within an accuracy of about 0.4%. In cosmology, flat does not mean thin or two-dimensional like a sheet of paper. It means that parallel lines never meet. Light travels along straight trajectories. The familiar rules of Euclidean geometry, the ones learned in school, still hold true even across distances of tens of billions of light years. Draw a vast triangle between three distant galaxies and the angles would sum to exactly 180 degrees. This idea did not emerge suddenly. It was first suggested by data from the Wilkinson Microwave Anisotropy Probe in 2003 and later confirmed in exquisite detail by Planck. Both missions measured the curvature of space by comparing the apparent size of temperature fluctuations in the early universe with theoretical predictions. The agreement was striking. Space is not curved like the surface of a sphere, nor warped like a saddle. It appears delicately balanced between the two, and yet that very perfection feels unsettling. Gravity, after all, bends space wherever mass exists. Galaxies, dark matter, even beams of light, all curve space-time around them. How then can a universe filled with billions of galaxies look flat overall? The explanation may lie in one of the most profound ideas in modern cosmology, cosmic inflation, proposed in 1981 by Alan Guth. Inflation suggests that in the first tiny fraction of a second after the Big Bang, roughly 10 to the power of minus 36 seconds, the universe expanded at an extraordinary rate, far faster than light itself. Such an expansion would have ironed out any initial curvature stretching space so dramatically that it would appear flat to any observer within it. Much as the curved surface of Earth seems flat when you stand upon it, the cosmos could look flat simply because we are seeing only a small portion of a vastly stretched geometry. NASA's cosmologists often summarize it this way: inflation explains why the universe looks the same in every direction, and why any original curvature was pushed far beyond what we can observe. That observable boundary, the cosmic horizon, lies about 46.5 billion light years away, in every direction. Beyond it we cannot see, but we can still wonder. Planck's data also reveals subtle irregularities, tiny regions slightly warmer or cooler than expected. Some scientists suspect these anomalies could be hints of deeper structure, perhaps signs that the flatness we observe is only a local feature of a much larger curved reality. It might be a hypersphere or something even more exotic, where our observable universe is just one region among many. In 2019, a study published in Nature Astronomy by cosmologists Alessandro Melchiori and Eleonora Di Valentino revisited the Planck data and suggested there could be a small positive curvature, implying the universe might be slightly closed, like a vast four-dimensional sphere. Yet subsequent analyses that combine data from baryon acoustic oscillations and supernova observations reinforce the conclusion that space is flat to within about 0.2%. If curvature exists, it is extraordinarily small. To understand what curvature truly means, it helps to picture simple shapes. Draw a triangle on the surface of Earth, start at the equator, travel north to the pole, then return along a different meridian. The angles of that triangle add up to more than 180 degrees. That is positive curvature. On a saddle-shaped surface, the angles would add up to less than 180, which is negative curvature. In a flat universe, they sum to exactly 180. So far, every experiment we have performed points to that flat outcome. But flatness does not imply stillness. Space itself is expanding not into anything external, but within itself. Galaxies drift apart not because they are moving through space, but because the space between them is stretching. This was first discovered by Edwin Hubble in 1929 and later refined by missions that measured distant Type Ia supernovae and their redshifts. Today, this expansion is driven by something even more mysterious: dark energy. Dark energy is an unseen component that makes up about 68% of the universe's total energy. It behaves like a cosmic pressure, accelerating the expansion so that distant galaxies recede faster and faster over time. If this process continues, the geometry of the universe itself could change, potentially shifting away from flatness in ways we do not yet fully understand. NASA's upcoming Nancy Grace Roman Space Telescope, planned for launch later this decade, is designed to measure dark energy with unprecedented precision. Its goal is to determine whether cosmic acceleration remains constant or changes over time. If it evolves, that would suggest the very fabric of space is still changing beneath our observations. When cosmologists say the universe is flat, they mean it is flat within the limits of what we can measure. Beyond those limits, uncertainty reigns. Our observable universe may be only a small patch on the surface of a far larger, curved, higher dimensional space, what some theories refer to as the bulk. Ideas inspired by string theory and brain cosmology explore such possibilities. Carl Sagan once remarked that the universe is not required to be in harmony with human ambition. Perhaps flatness is not a final answer, but a boundary marking the edge of our current understanding. Beyond that boundary, curvature could bend light, distort time, or connect distant regions in ways we have yet to imagine. There may be further clues hidden in gravitational waves, ripples in space-time, first detected in 2015. As these waves travel across billions of light years, their shapes encode information about the geometry of space itself. So far, they too are consistent with a flat universe. But future detectors, including the LISA mission, planned for the 2030 seconds, will listen to lower frequency waves and may one day uncover subtle deviations. What makes this question so powerful is that it links the smallest scales of quantum physics with the vast structure of the cosmos. The same equations that describe planets orbiting a star also describe how space bends under gravity. It is all geometry, but on scales so immense that we must infer their shape by looking deep into the past. Every photon of the cosmic microwave background has journeyed for 8 billion years, stretched by expansion and gently deflected by galaxies and voids along its path. When Planck measured those photons, it was not merely detecting ancient light, it was revealing the architecture of space itself. And even if the universe is truly flat, that does not necessarily mean it is infinite. It could be finite yet unbounded, like the surface of a sphere extended into higher dimensions. You could travel forever in one direction and eventually return to your starting point, not through ordinary three-dimensional space, but along a higher dimensional curve, beyond direct perception. Recent observations from the James Webb Space Telescope add another layer to this mystery. They reveal massive, surprisingly mature galaxies forming just 300 million years after the Big Bang. Such structures challenge existing models of how quickly matter clustered and raise questions about whether space itself might possess local curvature that inflation did not entirely erase. So when we ask whether the universe is round or flat, we are really asking a deeper question. What is space? Is it an endless plane unfolding forever, or the curved surface of a vast cosmic bubble? Is it truly flat, or does it only appear so because we see such a small fraction of it? As one NASA scientist beautifully expressed, the universe is not only stranger than we imagine, it is stranger than we can imagine. Each measurement, each map, each photon brings us closer to understanding, yet the shape of everything may still lie hidden beyond the cosmic horizon. And if our visible universe is merely one curved fragment of something far greater, then whatever exists beyond that horizon may not only bend space, but reshape reality itself. Because if the universe can be flat, round, or somehow both at once, then perhaps what we call flatness was never the full truth to begin with. Part 5. What if the idea of flatness is itself misleading? What if everything we observe, every line we draw, every plane we imagine, every horizon we trust, is only a tiny patch on something enormous and gently curved beyond our intuition? What if the universe appears flat simply because we are standing too close to its surface to notice the bend? We describe planets as round, galaxies as flat, and space as infinite. But these descriptions arise from a narrow perspective, the perspective of small beings confined to a small world. From a higher dimensional viewpoint, even the flattest spiral galaxy could loop back on itself, tracing a curve so subtle that it would take trillions of light years to complete. The universe may not be an endless straight road, but a closed journey that we mistake for infinity. This is not speculation or poetic fancy. It is one of the most serious ideas in modern cosmology. In 2018, researchers studying data from the Planck satellite suggested that the universe might in fact be slightly curved, perhaps shaped like an immense hypersphere, a four-dimensional analogue of a sphere. In such a cosmos, moving straight ahead for long enough could in principle return you to where you began without ever changing direction. To see why this matters, we need to return to one of the cornerstones of modern physics, Einstein's general theory of relativity. Einstein revealed that gravity is not a force acting across space. It is the geometry of space itself, molded by mass and energy. As he wrote in 1916, matter tells space how to curve, and space tells matter how to move. That curvature is not confined to local regions. On the largest scales imaginable, it determines the shape of the entire universe. If the total density of the universe, the combined amount of matter and energy in all forms, sits exactly at a critical value, then space is flat. If that density is higher, gravity dominates and the universe curves inward like the surface of a sphere. If it is lower, expansion wins and space curves outward like a saddle. Observations from the WMAP and Planck missions show that our universe lies extremely close to this critical density. But close is not the same as exact. The Planck analysis allows for a curvature radius so vast that even across the observable universe, about 93 billion light-years across any deviation from flatness would be imperceptible. Imagine standing on the surface of the Earth. To your senses, the ground appears perfectly flat because the planet's curvature is too gentle to notice. Only after travelling thousands of kilometres does the curve of the horizon become clear. Space itself may be the same. The universe could be curving softly in every direction, yet on scales so enormous that no telescope, not even the James Webb Space Telescope, can detect it directly. The Planck mission measured the curvature parameter omega to be roughly 0.007, with an uncertainty of about 0.0019. This implies that if the universe is curved, its radius of curvature is more than 250 times larger than the radius of the observable universe. That corresponds to more than 11 trillion light-years, a scale so immense that the cosmos appears flat by comparison. And yet there are clues. The cosmic microwave background, the ancient afterglow of the Big Bang, contains delicate asymmetries, temperature variations, and alignments that do not sit comfortably within a perfectly flat model. Features such as the cold spot may be hints of curvature or of massive structures that distort the background light as it journeys toward us. Cosmologists explain that light from the early universe does not travel along perfectly straight paths. Instead, it threads its way through gravitational wells, clusters, filaments, and vast voids, bending slightly at every encounter. This phenomenon, known as gravitational lensing, subtly reshapes the patterns in the microwave background, offering glimpses of the hidden geometry beneath. If we could step outside our three-dimensional viewpoint and see the universe as it truly is, it might resemble a hypersurface arcing through a higher dimensional space. In theoretical physics, this concept appears in models such as brane cosmology, inspired by string theory, where our entire universe could be a three-dimensional brane embedded within a larger, multi-dimensional arena. Gravity, unlike the other fundamental forces, may seep into these extra dimensions, which could explain why it appears so weak compared to electromagnetism or the nuclear forces. Experiments at the Large Hadron Collider at CERN have searched for signs of these extra dimensions by hunting for missing energy in high-energy collisions, possible evidence of gravitons escaping into higher space. So far, no direct signals have been found, but the constraints grow tighter, indicating that if extra dimensions exist, they must be smaller than 10 to the power of minus 18 meters, an unimaginably tiny scale. Even so, the mathematics is elegant. A galaxy like the Milky Way, which appears flat, could actually reside on a curved hypersurface. In the same way that a sheet of paper can be rolled into a cylinder or shaped into a sphere, it feels flat locally while bending globally. This contrast between local flatness and global curvature is one of the most beautiful outcomes of general relativity. Astronomers often describe it this way. Space can feel flat in our immediate surroundings while curving on the largest scales, just as the Earth feels flat beneath our feet, yet curves all the way around the planet. If this is true, then flatness is not an absolute property, but a scale-dependent illusion, a consequence of our smallness relative to the universe's true extent. The James Webb Space Telescope is now looking farther back in time than any observatory before it revealing galaxies from when the universe was less than 300 million years old. These early galaxies appear surprisingly massive and well organized, hinting that space itself may have evolved in unexpected ways, perhaps with variations in curvature across the cosmic web. That web, the immense network of filaments linking galaxies, also suggests curvature. Simulations show that gravity draws matter into these filaments, while dark energy stretches space between them, producing the appearance of straight lines across a universe that may as a whole be curved. At every scale, we examine geometry shifts. The solar system seems nearly flat because the planets orbit in roughly the same plane. The Milky Way looks flat because rotation spreads its material into a disk. But step back far enough to clusters, filaments, and voids, and that flatness dissolves into a curved cellular foam of matter and emptiness. Einstein once observed that the curvature of space is simply the manifestation of the gravitational field. This means that every star, every galaxy, and every trace of dark matter contributes to bending the cosmic fabric, weaving a vast tapestry of subtle distortions. Even if we cannot see the curve directly, its signatures appear everywhere in the way light bends, time flows, and galaxies move. One of the most powerful tests comes from baryon acoustic oscillations, ancient sound waves from the early universe, now preserved in the large-scale distribution of galaxies. By measuring their apparent size at different distances, scientists can infer the shape of space itself. So far, surveys such as EBOS and DESI confirm a universe that is very nearly flat, but nearly is not the same as perfectly. The illusion may persist simply because we cannot yet see the full arc of the curvature. The Nancy Grace Roman Space Telescope, planned for the latter part of the 2020s, will map these oscillations with extraordinary precision across billions of galaxies. Its observations may finally tell us whether flatness truly holds or whether space begins to bend beyond our observable horizon. If the universe is curved, it would reshape our understanding of everything from the nature of dark energy to the ultimate fate of the cosmos. A flat universe expands forever. A spherical one might eventually collapse. A saddle-shaped universe could expand endlessly but fragment into isolated regions. Each possibility leaves a distinct imprint on the cosmic microwave background, a faint record of geometry itself. And yet even if space is flat, reality may not be. Quantum mechanics describes another kind of curvature, not in space but in probability, where particles exist in multiple states until observed. Some physicists believe that these two geometries, the quantum and the cosmic, will one day unite in a deeper theory, revealing that flatness, curvature, and even the number of dimensions are not fundamental but emergent. Perhaps flatness is simply the smooth face of a deeper structure, folded in ways we cannot yet perceive. We may be living on the inner surface of a vast cosmic balloon, watching light glide across it, without ever grasping the full curve that supports us. Carl Sagan once said that we live on a mote of dust, suspended in a sunbeam. Were he here now, he might add that this mote is riding a curve so immense that no line we draw can ever be truly straight. Because the more precisely we measure the universe, the more we discover that geometry, the simplest of sciences, conceals the deepest secrets. What appears flat may be curved. What appears curved may be part of something even larger. Perhaps the illusion is not space itself, but the narrowness of our view. And if the universe truly folds around us, then every curve and every bend must lead somewhere. Maybe beyond those folds lies the shape that gravity has been tracing all along, a shape that echoes again and again throughout the cosmos. Part 6. Why does the universe so consistently return to roundness? Wherever we turn our gaze, the same form emerges again and again. From droplets of water floating freely in weightlessness to stars collapsing under their own immense gravity, matter left to itself almost always becomes round. The question is why? Why does this particular shape triumph over all others that nature might attempt? The answer begins with balance, one of the most relentless principles in physics. In the emptiness of space, stripped of air friction or external pressure, only gravity remains, and gravity acts impartially, pulling inward from every direction at once. That single simple rule makes the sphere unavoidable. As scientists probe deeper into the workings of the cosmos, it becomes clear that roundness is not an aesthetic choice. It is the direct outcome of physical laws operating without obstruction. A sphere is unique because every point on its surface lies at the same distance from its center. For that reason, it represents equilibrium, the lowest energy state available to any object bound by its own gravity. As NASA physicist Jeffrey Landis once observed, a sphere is the natural form adopted by anything seeking to minimize potential energy. In that sense, roundness is not selected, it emerges. It is what appears when competing forces stop resisting one another and settle into agreement. Consider the smallest scales first. In microgravity experiments aboard the International Space Station, when astronauts release a droplet of water, it instantly pulls itself into a near-perfect sphere. Gravity plays almost no role here. Instead, surface tension dominates the attraction between molecules that works to reduce surface area. Of all possible shapes, a sphere encloses the greatest volume using the least surface, making it the most energy-efficient option available to nature. Now expand that idea to planetary scales. A planet follows the same logic, but with gravity taking the place of surface tension. When a rocky body grows to roughly 600 kilometers in diameter, its gravity becomes strong enough to overcome the rigidity of its material. Peaks collapse, depressions rise, and across millions of years the object slowly reshapes itself into a sphere. This state, known as hydrostatic equilibrium, separates planets from smaller bodies. Ceres, the largest object in the asteroid belt, is round, precisely because it reached this threshold. Smaller asteroids, such as Eros or Itokawa, remain misshapen in their gravity, too weak to smooth their jagged outlines. On an even grander scale, the same principle governs stars. As a star forms, gravity pulls inward, while energy from nuclear fusion pushes outward. This delicate standoff, called hydrostatic balance, keeps stars like our Sun spherical. When that balance collapses, the shape changes. Stars can compress into neutron stars or black holes, where gravity ultimately dominates. Our own Sun is astonishingly round, differing by less than 10 kilometers between its equatorial and polar diameters, despite spanning nearly 1.39 million kilometers across. Observations from NASA's Solar Dynamics Observatory revealed in 2012 that the Sun is among the roundest natural objects ever measured. Absolute perfection, however, is rare. Rotation introduces distortion. Just as Earth bulges slightly at its equator because of its daily spin, faster rotation exaggerates this effect. Saturn, for example, completes a rotation in about 10 hours, causing its equatorial diameter to be roughly 10% larger than its polar diameter. Even so, from afar, it still appears unmistakably round. The visible forms of celestial objects are shaped by a constant contest between gravity, which smooths and compresses, and rotation, which stretches and flattens. Together, they sculpt worlds that are never flawless, yet always striving towards symmetry. The European Space Agency's Gaia spacecraft has mapped the precise shapes of hundreds of thousands of stars. Some are slightly flattened, others stretched by strong magnetic fields or tidal interactions with companion stars. And yet, across all these variations, the same pattern holds. Left undisturbed, stars gradually relax back toward roundness. Nature repeatedly returns to balance. This applies equally to gas giants, neutron stars, and even black holes. According to Einstein's equations, a non-rotating black hole is a perfect sphere of curved space-time, perhaps the most extreme expression of roundness in the universe. Add rotation, and the shape distorts slightly, but its underlying symmetry remains intact. Even where light itself cannot escape, geometry still obeys the same rule. What makes this truly remarkable is how universal the pattern is. The same laws that shape a droplet of water also shape a planet, differing only in scale. As Richard Feynman once remarked, everything is made of the same stuff and follows the same rules. That consistency offers a quiet reassurance. From atoms to galaxies, structures across the universe pursue the same destination: minimum energy and maximum balance. This is why even chaotic systems, given enough time, drift towards symmetry. Roundness prevails, because it represents the natural resolution of disorder into order. Scientists at NASA's Jet Propulsion Laboratory often describe this as the slow refinement of chaos. Over billions of years, gravity wears down irregularity, eroding mountains, collapsing clouds of dust, and smoothing the sharp edges of creation. Every world we observe is a snapshot of that struggle, paused somewhere between compression and expansion. Even on Earth, roundness reveals itself in unexpected ways. Raindrops falling through the atmosphere form spheres under the influence of surface tension until wind resistance deforms them. Lava, bubbles, ocean currents, and even living cells follow the same geometric logic. The shapes of life and stars are not as distant as they appear. Both are governed by the mathematics of equilibrium. The dominance of roundness extends beyond individual objects to the evolution of the universe itself. After the Big Bang, as the cosmos cooled, gravity drew matter into spherical concentrations that became the seeds of galaxies. Dark matter, unseen yet massive, formed nearly spherical halos around them, guiding their growth. Computer simulations show these halos remain almost perfectly round even billions of years later. These rounded gravitational cores provide the stability that allows flat rotating galaxies like the Milky Way to exist. Beneath every disk lies a spherical foundation. Without it, galaxies would be torn apart by collisions or rotational forces. No matter how complex the interactions become, the outcome remains consistent. The universe favors smoothness, not metaphorically but mathematically. Even the cosmic microwave background, the oldest light we can observe, reflects this tendency. Its temperature varies by less than a tiny fraction of a percent, a signature of a universe moving toward balance from its earliest moments. Roundness, then, is not merely a shape, it is a record evidence of forces cancelling out over time. It is the geometry of rest expressed through energy. Yet the process is ongoing. Asteroids collide, planets wobble, stars erupt, and galaxies merge. Each disturbance breaks symmetry, and each time gravity begins its work, again drawing matter back toward its preferred form. The universe does not forbid motion, it corrects it. It has been said that the universe owes us no explanation, and yet through this persistent return to roundness, it reveals a quiet logic. The same symmetry that shapes planets also governs atoms. The same stability that molds a droplet shapes the sundae. From the faint cloud of an electron to the vast web of galaxy clusters, the rule repeats itself. Left alone, matter always follows the path of least energy, and that path is round. Gravity is the ultimate organizer. It dissolves complexity and favors simplicity. So when we look through a telescope and see a world traced as a perfect arc against the darkness, we are witnessing the final moment of a long correction, the conclusion of a cosmic negotiation. Every planet is a quiet triumph of physics. Every star is a conversation between gravity and pressure that ended in agreement. Roundness keeps prevailing because it is not competing at all. It is the destination. It is what remains when every other force has exhausted its argument. And yet there are regions of the universe where this balance begins to falter, where rotation overwhelms gravity and symmetry fractures into flattened, turbulent forms. What becomes of roundness there? What new shapes arise when motion refuses to settle? Part 7. Why does the cosmos seem so hostile to sharpness? If the fundamental rules of nature had been written differently, we might look up at a night sky crowded with cubes. Worlds shaped like boxes orbiting angular stars. Moons like pyramids casting crisp, triangular shadows across the void. Yet that is not the universe we inhabit. Everywhere we observe, from the smallest bead of liquid to the most massive star matter, drifts inevitably towards smooth forms. No corners, no edges, no true exceptions. At every scale, the universe reveals a preference for roundness. Spheres, ellipses, spirals, the same gentle geometry repeating itself across existence. The mystery is not simply why objects become round, but why sharpness itself fails to endure. The answer is found in the most ancient sculptor of all, gravity. Unlike human tools that cut and carve, gravity does not strike or chisel. It permeates. Every atom, every particle feels its influence evenly from all directions. Given time, that uniform pull wipes away irregularities, transforming disorder into balance. Astronomers often refer to gravity as the great leveler. It shows no favoritism, recognizes no angles, and carries no bias. Its only aim is to reduce energy. And in the language of physics, the lowest energy configuration for a self-gravitating object is always the same, a sphere. Begin with our own planet. On Earth, mountains rise, continents wander, volcanoes tear through crust and stone. Yet over long spans of time, even the highest summit yields to its own weight. The process is gradual, but it never relents. Erosion, tectonic motion, and gravity collaborate to soften every sharp feature nature dares to create. The same principle governs planets and moons. When a rocky body grows beyond a certain size, usually around 600 kilometers across gravity, overwhelms the strength of the material itself. Peaks collapse inward. Depressions rise. The object reshapes into a sphere. This boundary is known as hydrostatic equilibrium. The moment a world becomes round because it has no other choice. The Dawn mission provided a striking example when it visited the dwarf planet Ceres. Once an irregular assembly of rock and ice, it now rests in near-perfect symmetry. A rounded world formed through millions of years of quiet adjustment. Its shape is not chance. It is physics expressed as inevitability. Asteroids tell a different story. Too small for gravity to fully dominate, they retain their roughness. Jagged, uneven, defiant. But those sharp edges are meaningful. Every crater and fracture records a moment gravity has not yet erased. When the OSIRIS-REx mission reached Bennu, scientists encountered a loose rubble-like body with an uneven form poised between disorder and order. Over immense stretches of time, Bennu will collide, spin, or slowly reshape itself, inching closer to the same smooth fate that awaits all matter. This pattern repeats even at microscopic scales. Water droplets, oil bubbles, living cells all become spherical when freed from external forces. The reason is surface tension. It lowers energy by minimizing exposed area, compelling liquids toward roundness. The distinction between a droplet and a planet is one of scale, not principle. Nature resists imbalance. Everything seeks equilibrium. Sharp edges represent gradients, regions of concentrated stress. Such concentrations do not last. They gather force, heat, pressure. The universe does not preserve them for long. In stars, this rule is unmistakable. Inside the Sun, plasma roils at 15 million degrees, yet immense pressure maintains balance. Gravity pulling inward is matched precisely by the outward force of fusion. This equilibrium produces near-perfect roundness, smoother than anything we could manufacture. Jupiter obeys the same law. Despite storms larger than Earth and winds racing hundreds of kilometers per hour, its gravity holds it close to spherical. Only its rapid rotation slightly flattens it at the poles, a reminder that motion can stretch symmetry but not destroy it. This preference for smoothness extends far beyond planets. Stars, galaxies, clusters of galaxies all curve gracefully shaped by gravity's unseen influence. Observations from the James Webb Space Telescope reveal galaxies formed when the universe was less than 500 million years old, already displaying spirals and ellipses. The smoothing began early. Yet the universe is not gentle by nature. It is violent, chaotic, marked by impacts, explosions, collisions, meteor strikes, supernovae, black hole mergers, all introduce disorder. But disorder is temporary. Gravity is patient. It returns again and again to erase the marks. That is why telescopes reveal no cosmic shards, only orbs, halos, spirals, clouds. Even on the largest scales, the rule persists. The cosmic microwave background, the oldest light we can observe, is almost perfectly uniform in every direction. Its temperature varies by less than 1 part in 100,000. This extraordinary smoothness shows how swiftly gravity erased the sharp fluctuations of the early universe. Tiny ripples remained to seed galaxies, but overall, the cosmos settled into balance. So why does the universe reject sharp edges? Because edges are unstable. They represent high energy states. Sharp angles concentrate stress, and stress is stored energy waiting to escape. Physical systems naturally move toward lower energy. That descent always favors smoothness. Even the mathematics reflects this truth. General relativity describes mass and energy as curving space-time, and that curvature is continuous. True corners would fracture the equations themselves. In a very real sense, space-time cannot sustain sharpness. Laboratory experiments confirm this. From rotating fluids to exotic quantum systems, when left undisturbed, patterns evolve towards smooth, rounded forms. Permanent edges do not exist in physics, only temporary distortions. Studies of black holes confirm this at the extreme. When two black holes merge, the result vibrates, shedding irregularities as gravitational waves. Within moments, the final object becomes smooth again, perfectly round in space-time geometry. Gravity smooths everything. It is how the universe enforces calm. That calm is not stillness. It is motion in balance. The same equilibrium that shapes stars governs droplets, tides, gases in nebulae. The forms vary, but the tendency remains towards symmetry, towards softness. From a thermodynamic perspective, sharp edges are rare because systems evolve toward entropy, the most probable distribution of energy. Uneven shapes concentrate energy. Smooth shapes reflect balance. Given enough time, everything rounds out. Asteroids soften through impacts. Planets settle into spheres. Stars stabilize into symmetry. The timescales may span billions of years, but the direction never changes. The atoms that make up our bodies were forged in spherical stars, shaped by the same gravity that binds Earth. When we observe the roundness of worlds, we are witnessing matter learning how to rest. Even now, as we peer billions of light years away, no true edges appear. Curves dominate, absolutely. Sharpness is a human invention. Smoothness is written into the laws of physics. The cube is a decision. The sphere is unavoidable. But as unseen forces continue to shape the cosmos, as motion itself becomes the sculptor, one question remains. Can anything remain perfectly round forever? Or does even symmetry eventually begin to tremble under time? Part 8. What unseen influence gives rise to every sphere we observe? If the cosmos were guided by an artist, it would never rely on tools or blades. Its medium would be gravity. Quiet, unseen, and endlessly patient. Gravity is the subtle presence that gives form to everything from a drifting bead of water to a blazing star. Every celestial body we know owes its shape to this restrained force. It draws planets into spheres, anchors oceans to worlds, and assembles entire galaxies into luminous halls. Without it, there would be no paths traced in the sky, no stars burning, no harmony. Only scattered dust suspended in eternal calm. But what truly is gravity? In Einstein's general theory of relativity, gravity is not a force, as we once imagined. It is the bending of space-time itself, shaped by mass and energy. Matter tells space how to curve, and curved space tells matter how to travel. The greater the mass, the deeper the bend, and that bending at every scale naturally produces roundness. Picture a stretched fabric. Place a heavy sphere upon it, and the surface dips, curving inward. Set smaller balls nearby and they roll toward it, not because they are pulled by some hidden thread, but because the surface beneath them is shaped. That is gravity in action, not as a tug, but as geometry. Astrophysicists often describe it simply. Gravity is geometry set in motion. It molds matter through attraction, drawing everything toward a shared center of mass. Given time enough, any gathering of particles settles into a sphere, because only that form allows every inward pull to balance completely. Now consider how this unseen sculptor operates across scales. Begin with something small, a droplet of water released in microgravity. Aboard the International Space Station, astronauts have captured this moment. The water instantly gathers into a floating sphere. The molecules pull evenly in all directions through surface tension, reducing energy and surface area. That is nature seeking calm. Gravity applies the same principle on far grander scales. Enlarge that droplet a millionfold. In space, clouds of dust and gas begin to draw together. Over thousands of years, they form planetesimals, and over millions more, they grow into protoplanets. When their own gravity overwhelms the strength of solid rock at roughly 600 kilometers across, they yield and become spherical. That moment marks the birth of a world. This balance is known as hydrostatic equilibrium. When inward gravitational pull and outward pressure align, the body becomes round enough to be considered a planet. This is why Ceres is spherical, while smaller bodies like Phobos remain irregular. The rule applies everywhere. Jupiter, the giant of our solar system, is almost perfectly round, a vast globe of gas, compressed by its own gravity. Even with violent storms and rapid rotation flattening it slightly at the poles, its shape remains governed by equal pressure in every direction. Gravity is also the reason the sun shines. As hydrogen collapses under its own weight, the core grows hot and dense enough for fusion to begin. Fusion pushes outward, gravity pulls inward, and the star settles into balance, a sphere poised between collapse and eruption. Measurements taken in 2012 showed the sun's equatorial diameter exceeds its polar diameter by only 10 kilometers, a deviation of less than 1 part in 100,000. Scaled down to the size of a beach ball, that difference would be thinner than a human hair. The sun is among the roundest objects we have ever measured. Yet gravity's craft extends beyond stars. On the largest scales, it designs galaxies themselves. Through slow accretion, dark matter halos gather ordinary matter, shaping it into spirals, ellipses, or spheres, depending on motion and density. Observations have revealed such structures forming just 300 million years after the Big Bang. Even then, gravity was already tracing familiar curves across the infant universe. Detailed maps of the Milky Way show subtle bends and waves caused by the gravitational interplay between the galactic core and its spiral arms. Every curve recorded is matter moving toward balance, another quiet gesture of cosmic design. Einstein's equations foresee this tendency. When matter collapses symmetrically under gravity, a sphere emerges. When collapse becomes extreme, as in the death of a massive star, gravity compresses the core into a black hole so dense that light itself cannot escape. The boundary of that darkness, the event horizon, is always spherical. Even absence must obey the geometry of space-time. From the tiniest bubbles to the largest galaxies, the same principle resonates. Gravity removes preference. It does not choose up or down, left or right. It chooses unity. That is why across billions of years, uneven forms are softened and smoothed, drawn inward toward their own center, like a breath settling into stillness. One astronomer once wrote that the cosmos is everything that ever was or will be. And within that vastness, gravity is the one rule that never falters. It does not contest chaos. It simply waits longer than chaos can last. Other forces may intervene. Magnetism can twist plasma into filaments. Explosions can scatter matter into jagged clouds. But as energy fades, gravity resumes its work, slowly rounding debris into balance. Even relics of ancient violence like the moon have become smooth and whole through ages of quiet settling. Direct exploration confirmed this dominance. The moon bears countless scars, yet as a whole it is round. Each impact leaves a mark, but none override the deeper symmetry imposed by mass and gravity. Local disorder persists, but global order remains. And this sculptor has not finished. It continues shaping the universe now. Galaxies collide, stars ignite and expire, planets wander, yet the same curvature returns, written into every new form. At the heart of every equilibrium lies gravity. It has no sound, no color, no presence we can touch, yet it defines the structure of all that exists. It governs orbits, raises tides, and sets the tempo by which galaxies turn. Gravity is the closest thing the universe has to a signature, a rule linking every atom to every star. The curve of a droplet, the shape of a world, the arc of a galaxy, all arise from the same quiet equation unfolding without end. To understand gravity is to glimpse the hidden framework of reality. It is more than what holds us to the ground. It is what binds everything together. The same principle that may one day draw galaxies into stillness or drive them apart if expansion prevails. Every curve in the night sky, every moon and planet, every ring encircling Saturn is written in gravity's script. And though it has no face or voice, its work surrounds us. When you look up at a full moon hanging perfectly round against the dark, you are seeing the oldest artwork in existence, shaped not by hands, but by time itself, and the invisible insistence of gravity. Yet even this sculptor encounters limits. What happens when motion resists, when rotation accelerates until gravity begins to yield? What new forms emerge when balance itself starts to bend? Part 9. Why is it impossible to make a triangular soap bubble? You can try it yourself. Bend a piece of wire into a triangle, a square, even something wildly irregular. You can hold that shape in your hands quite easily. But the moment you dip it into soapy water and let a bubble form, the film refuses to obey your intentions. It curves inward, softens every angle, and settles into something smooth. Nature quietly ignores your corners. And the reason is profound, because the same principles shaping this fragile bubble also govern planets, stars, and galaxies. Surface tension is, in a sense, gravity at a much smaller scale. It draws liquid molecules toward one another, relentlessly seeking the lowest possible energy state. In physics, there is a simple truth. For a given volume, the shape with the smallest surface area, the most efficient and stable configuration, is the sphere. That is why every soap bubble, the instant it forms, becomes round. The shape of the frame does not matter. Triangle, cube, star. The film reorganizes itself, redistributing tension until balance is achieved. Corners disappear, edges dissolve, energy spreads evenly across the surface. This is not chance or preference. It is mathematics. A sphere exposes the least surface to the outside world for the same amount of material. And that is why droplets, planets and stars, despite existing on vastly different scales, all converge on this same geometry. Physicists describe this tendency as energy minimization. Nature does not expend effort unnecessarily. From molecules to galaxies, systems evolve towards states that require the least energy to sustain. There is no decision involved. It is simply how the universe works. To see this more clearly, consider what a soap bubble actually is. Its surface is an extraordinarily thin film, only a few hundred nanometers thick, composed of water trapped between two layers of soap molecules. Each soap molecule has a dual personality. One end is attracted to water, the other repelled by it. This creates a flexible membrane capable of holding air. As you blow into the film, pressure builds inside. Expansion increases surface tension until an equilibrium is reached. The outward push of the air exactly balances the inward pull of the surface. The outcome is a perfect sphere, the only shape where every point on the surface experiences the same stress. This principle is so fundamental that it becomes even clearer in space. Scientists study fluid behavior in microgravity aboard the International Space Station, where gravity no longer flattens liquids. There, water naturally gathers into floating spheres. Astronauts have recorded mesmerizing footage of drifting globes of water rotating gently, preserving their round form regardless of motion. It is physics in its purest expression, energy seeking balance. One astronaut once remarked that in microgravity, water behaves as though it wants to become a planet, and that is precisely the point. The equation governing a droplet also governs a star. Both are shaped by the balance between internal pressure and an inward pull. If a soap bubble were somehow enlarged to planetary size, the same forces would be at work, pressure pushing outward, a surrounding force pulling inward. This balance keeps Earth round, stabilizes the Sun, and maintains the spherical form of neutron stars, spinning hundreds of times each second. Yet within this simplicity lies extraordinary complexity. Look closely at a bubble, and you see shimmering bands of color sliding across its surface. These colors are not pigments. They are the result of light interference. Light waves, reflecting from the inner and outer surfaces of the film, overlap, reinforcing or cancelling one another depending on thickness. What you are seeing is physics made visible, light painting the changing structure of the film. Soap films are even used to model cosmic behavior. Researchers study how thin films move, drain, and redistribute tension to better understand how gases and plasmas flow through stars and nebulae. The same mathematics links bubbles to vast clouds of interstellar matter. Even in space, surface tension plays a role. When two droplets meet in microgravity, they instantly merge into a larger sphere, releasing excess energy as heat and vibration. It mirrors how galaxies collide, stars fuse, and planets accumulate mass. Complexity simplifies itself into unity. This is also why angular shapes cannot survive under these conditions. Edges focus tension, corners amplify stress. A triangular bubble would fail immediately because molecules at the corners would exist in a higher energy state. And nature, always efficient, removes that imbalance, right? Even when scientists attempt to force angular forms, the universe resists. Soap films stretched across wire frames will always find the shortest possible path, what mathematicians call a minimal surface. These films curve elegantly, forming shapes like catenoids and helicoids, but never flat polygons. The study of minimal surfaces, explored since the 18th century, has influenced fields far beyond soap bubbles. It explains how energy moves through networks, why DNA coils smoothly instead of folding sharply, and even how space-time itself may curve under mass. From droplets to galaxies, every surface follows the same rule. The lowest energy path is always the smoothest one. Entire galaxies have been modeled using these equations. The graceful spiral arms of the Milky Way are not accidental. They emerge from matter, minimizing energy while conserving angular momentum. In that sense, a galaxy is a cosmic soap bubble made not of air but of stars. And yet, even a bubble carries the seed of its own end. Just as stars exhaust their fuel and planets cool, every bubble eventually bursts. Evaporation thins the film until it can no longer support the pressure within. The collapse happens almost instantly, but even this ending follows precise laws. High-speed footage reveals the edge snapping back at remarkable speeds, curling inward as surface tension reclaims the liquid. The same equations describe collapsing stars and supernova shockwaves. Different scales, identical physics. Energy always seeks equilibrium. Whether in a dying bubble or a fading star, the same quiet logic unfolds. What builds tension must eventually release it. One pattern ends, another begins. To create something as simple and perfect as a soap bubble requires atoms, forces, and laws that govern the entire universe. Just as the cosmos does not permit triangular planets, it does not permit triangular bubbles. Both obey the same geometry. Smooth surfaces, balanced forces, evenly distributed energy. Every shape you see is gravity and tension meeting halfway. So when you watch a soap bubble drift through the air, you are not merely playing with soap and breath. You are holding a miniature reflection of the universe itself. A floating reminder that physics solves problems gently, efficiently, and always with symmetry. And if bubbles and planets obey the same rule, then perhaps the deepest structure of the universe is written in the same quiet equations that shape a fragile film of soap. Part 10. What form can hold the greatest amount within the smallest boundary? If the cosmos were asked to choose a shape to store all that, it makes a design that contains the most while using the least. It would always settle on the sphere. From drifting droplets to blazing stars, the answer is the same. This principle never fails. A sphere wraps the maximum volume with the minimum surface. It is efficiency made visible, a geometry the universe repeatedly returns to whenever nothing obstructs it. Physics is economical. It does not squander energy. Every process, from the faint tremble of an atom to the catastrophic collapse of a star, obeys a quiet instruction: reduce energy, increase stability. The sphere is the purest expression of that instruction. Picture a quantity of matter, gas, liquid, or dust suspended in space. Left alone, free of disturbance, gravity and molecular forces begin to act. Gradually, the material draws inward, searching for the most compact arrangement available. What emerges is not a cube or a disk, but a sphere. No other form can hold so much matter with so little exposed surface. In mathematics, this is known as the isoperimetric inequality. Of all shapes sharing the same surface area, the sphere encloses the greatest volume. It is one of the oldest truths in geometry and one of the most universal in nature, appearing everywhere from microscopic cells to entire planets. Consider a droplet of water in microgravity. Aboard the International Space Station, astronauts have shown that when water is released, it immediately becomes spherical. No edges, no corners, just the smoothest surface possible, because surface tension is relentlessly minimizing energy. The smaller the surface, the fewer molecules are exposed, and the lower the energy state becomes. That same physics operates on scales millions of kilometers wide. When clouds of dust and gas collapse under their own gravity, they assume a spherical form for precisely the same reason. It is the most efficient configuration matter can achieve under pressure. Within a planet or a star, every point on the surface lies at the same distance from the center. Forces inside balance perfectly. Scientists describe this condition as hydrostatic equilibrium, the moment when inward gravity and outward pressure match. That balance defines what it means to be a planet. Worlds like Ceres or Pluto are not round by chance or beauty. They are round because physics permits no better solution. When an object grows large enough, gravity overcomes the internal strength of rock or ice and compels it into a sphere. The shape is gravity's unmistakable signature, the point where resistance ends. Stars follow the same rule. Our sun, for instance, is extraordinarily round. Observations show that the difference between its polar and equatorial diameters is less than 10 kilometers, despite spanning more than 1.39 million kilometers across. That is a precision of about 0.007% smoother than anything humanity has ever constructed. Yet gravity alone does not tell the full story. Deep within the sun, pressure from nuclear fusion pushes outward with staggering intensity, hundreds of billions of atmospheres at the core. Gravity presses inward with equal strength. That balance, sustained for billions of years, keeps the sun stable, luminous, and spherical. If you could witness a star being born through the James Webb Space Telescope, you would see this principle unfolding. Inside dense nebulae like the pillars of creation, gas begins to collapse into glowing spheres of hydrogen plasma. Each begins irregular, shaped by turbulence and chaos, but as pressure rises, gravity smooths away every imperfection. The result is always the same. The quiet symmetry of a star, and this behavior is not confined to stars. Bubbles of plasma, droplets of oil, even living cells follow the same energetic law. A red blood cell, for example, adopts a nearly spherical form to maximize volume while minimizing interaction with its surroundings, an efficient way to transport oxygen through the body. Again and again, nature arrives at the same answer. Why does the universe favor efficiency so strongly? Because inefficiency cannot last. Excess surface means greater exposure, higher energy, and instability. A cube has edges and corners where stress accumulates. A sphere has none. It distributes stress evenly. It is stability embodied, every point equivalent, every direction balanced. Even on the largest scales, this rule endures. Measurements of the cosmic microwave background reveal that the early universe was astonishingly uniform, with temperature differences of less than 1 part in 100,000. That smoothness tells us that energy, even at the very beginning, was already spreading itself efficiently. That uniformity allowed gravity to gather matter into galaxies, stars, and planets. Without it, the universe might have shattered into disorder. Instead, it evolved into a structured, rounded, stable cosmos. When physicists model self-gravitating fluids, the outcome is always spherical. Whether simulating a nebula or a droplet of molten rock, the equations resolve towards symmetry. Even when rotation introduces distortion, the system relaxes into a slightly flattened sphere, still preserving volume with minimal surface. Within apparent chaos, this simple rule quietly maintains order. The same mathematics that describes the curve of a raindrop also describes the form of a neutron star. Efficiency does not stop at shape. In engineering and biology alike, this principle guides design. Bubbles, eggs, and cells are all examples of minimal surface structures. Human technology follows the same lesson. Pressure vessels, submarine hulls, and spacecraft tanks are made round because curvature spreads stress and resists collapse. The Orion spacecraft, for example, uses spherical tanks to store oxygen and hydrogen for exactly this reason. The sphere holds the most with the least material. It is not only elegant, it is practical. The same idea shapes galaxies. In the early universe, vast halos of dark matter formed roughly spherical concentrations of mass. These halos became gravitational wells, capturing gas and seeding galaxies. Even as galaxies spin into disks, the invisible dark matter framework remains rounded. Without it, galaxies would tear themselves apart. Step far enough back to view the cosmic web itself, the network of filaments and voids linking galaxies, and you would find local complexity but global balance. Energy always seeks uniformity. The architecture of the universe is a grand echo of the rule that shapes a bead of dew on a leaf. There is even a mathematical proof extending this dominance into any number of dimensions. The shape that minimizes surface area for a given volume is always a hypersphere, the higher dimensional analog of a sphere. Even in possible extra dimensions, symmetry and efficiency prevail. From this vantage point, roundness is not accidental. It is the inevitable outcome of physics optimizing itself. Energy flow, pressure gradients, and gravity all converge on the same solution: balance. When motion settles and equations come to rest, the form that remains is the sphere. Astronomers sometimes call it the shape of peace. A planet becomes round when its violent beginnings have calmed. A star's symmetry signals its maturity. In every sense, roundness marks equilibrium. The final form matter adopts when it stops resisting itself. Yet even this elegant rule has boundaries. Spin too fast, and a sphere flattens. Compress too far, and it may collapse into something far stranger: a ring, a torus, a black hole. Beyond those limits, efficiency yields to extremes. So the question lingers: if the sphere is nature's most perfect answer, what happens when that perfection begins to fail? When rotation, magnetism, or quantum effects drive matter beyond balance? Does the universe recover symmetry, or does it create entirely new forms? Part 11. Why is it that even pigeons seem to turn into perfect spheres when the cold arrives? When you step outside on a winter morning and notice a pigeon swelling into a soft, rounded mass of feathers, you are witnessing a principle that echoes across the universe. From birds gathered on city pavements to vast gas giants circling distant suns, anything that must endure the cold learns the same fundamental lesson: becoming round conserves energy. As temperatures fall, warmth becomes a precious commodity. Every warm-blooded organism must constantly negotiate between two opposing forces: how much heat it can produce and how much it loses to the surrounding air. In physics, this delicate trade-off is described by a remarkably simple relationship. The speed at which heat escapes depends on the ratio between surface area and volume. The idea is straightforward. The more surface you expose compared to what you contain inside, the faster heat is lost. Shapes that are flat or sharply angled shed warmth rapidly because so much of their area is open to the environment. A sphere, however, holds the same volume using the smallest possible surface. With less surface available, heat seeps away more slowly. This is why a cold pigeon fluffs its feathers and takes on an almost perfectly spherical form. In doing so, it traps a thin layer of air, one of nature's simplest and most effective insulators, close to its body. That trapped air slows heat transfer by conduction, forming a protective thermal shell, not unlike a planetary atmosphere. This small everyday scene mirrors processes that operate on the grandest scales. Planets and stars behave in much the same way, with gravity pulling material inward until it settles into a sphere, the configuration that conserves energy most efficiently. Thermodynamics captures this precisely. The Stefan Boltzmann law tells us that the energy radiated by a surface scales with the fourth power of its temperature. Even a modest reduction in exposed area can therefore dramatically slow the loss of energy. The implication is clear. The closer something comes to a sphere, the better it retains its heat. Birds are far from alone in exploiting this rule. Arctic foxes curl themselves into compact balls during blizzards. Penguins press together into dense, near-spherical huddles. Seals tuck their flippers beneath their bodies to reduce exposure. Each of these behaviors follows the same mathematical impulse: minimize surface area, protect volume, preserve the living core. This is not biology borrowing from physics. It is the universe expressing the same idea in multiple forms. The geometry that keeps a pigeon warm is the same geometry that stabilizes the heart of a planet. The principle that governs the surface of a droplet also shapes the outer layers of the sundae. Roundness is therefore not an aesthetic accident. It is a strategy for survival encoded in the laws of thermodynamics. Consider the Earth's atmosphere. It behaves very much like a layer of feathers trapping heat emitted by the surface, and spreading it around the planet. Without this gaseous blanket, Earth's average temperature would plunge from about 15 degrees Celsius to roughly -18. The atmosphere, like a bird's plumage, is nature's method of wrapping a world in warmth. The same logic applies to the giant planets, Jupiter and Saturn. Deep within their thick atmospheres, gases are compressed by gravity, trapping internal heat and sustaining a long-term balance. Despite receiving relatively little warmth from the sun, their spherical forms help regulate how they radiate energy, neither too quickly nor too slowly. This principle reaches even further, extending to stars themselves. Stars maintain an almost perfect spherical shape because the outward pressure from nuclear fusion balances the inward pull of gravity. The result is thermal stability and an orderly flow of energy from core to surface. The shape is not decorative, it is required. One physicist famously remarked that nature dislikes imbalance. Heat, pressure, and motion all evolve toward equilibrium. A sphere represents the ultimate state of that balance, where gradients are smoothed away in every direction. Look closely, and the same reasoning appears throughout biology. Polar bears, for instance, have smaller ears and shorter limbs than their relatives in warmer regions, an example of what biologists call Allen's rule. By reducing surface area relative to body mass, they limit heat loss. Their compact, rounded bodies are evolution following geometry. The pattern repeats even at microscopic scales. Spherical bacteria are among the most efficient forms for conserving resources and withstanding external stresses. Their surface to volume ratio minimizes losses through diffusion and maximizes the retention of energy. Physics defines the constraints, and evolution works within them. Now scale this up once more from pigeons to planets. As a planet forms, whether from rock, ice, or gas, its material responds to the same thermodynamic pressures. Gravitational energy draws matter inward until balance is achieved. The outcome is a rounded, self-stabilizing object, a cosmic analog of a bird drawing itself in against the cold. Even the cosmic microwave background, the faint afterglow of the Big Bang, reflects this tendency. It radiates almost evenly in all directions, with temperature differences of less than 1 part in 100,000. That extraordinary smoothness shows that the early universe itself was striving for thermal equilibrium, ironing out energy differences across space. Everywhere, nature is wrestling with the same question: how to contain the most using the least. Whether it is a snowball, a star, or a sleeping animal, the solution is identical: compress the boundaries, balance the pressures, conserve the energy. Scientists studying Europa, one of Jupiter's icy moons, have discovered that its rounded shape conceals a liquid ocean beneath the surface. Tidal heating and the insulating properties of the ice shell keep that ocean from freezing solid. Even water locked beneath ice and shaped by gravity finds a way to persist through form. So when you notice a pigeon puffed up on a wire, you are not just seeing instinct at work, you are seeing thermodynamics made visible. The bird becomes a living equation, adjusting surface and volume just as a planet balances gravity and pressure. That gentle curve of feathers is as rigorous scientifically as it is visually pleasing. The Stefan Boltzmann law, hydrostatic equilibrium, surface tension, and gravity all converge on the same conclusion: symmetry conserves energy. Across every scale, the universe favors roundness not by coincidence but by necessity. One writer once observed that the beauty of a living thing lies not in its atoms, but in how they are arranged. That arrangement almost always bends toward efficiency. From atoms to entire worlds, nature organizes itself to conserve rather than squander. Even in the technologies we build, the same principle emerges. Engineers design pressure vessels, submarines, and spacecraft with rounded or spherical forms because they distribute stress evenly, using less material while enclosing more space. A pigeon inflating its feathers and a capsule circling Earth are both responding to the same underlying mathematics. There is something reassuring in recognizing how deep this connection runs. Every curve in a bird's plumage, every swirling cloud on Jupiter, every distant exoplanet silhouetted against its star is evidence of physics quietly maintaining balance. Yet balance is never eternal. Eventually pressures change, energy escapes, and motion resumes. Even the most spherical star will one day expand, distort, or collapse. Even the warmest creature must confront the cold. And when equilibrium fails, when energy can no longer be contained, the universe invents new shapes, new patterns, and new forms of order emerging from disorder. What happens then when the cold truly takes hold, not just on Earth, but throughout the cosmos? Part 12. How does gravity coax a sphere out of raw stone? If you could witness a planet coming into existence, not across days or lifetimes, but over millions of quiet, unhurried years, you would observe one of nature's most deliberate transformations. A rough, chaotic mass of rock gradually yields, settles, and smooths itself into something entirely different, a sphere. This is the way gravity, the universe's most understated sculptor, converts debris into worlds. At the beginning, there is nothing elegant about the process. The early solar system was a turbulent arena. Vast clouds of dust and ice slammed into one another at enormous speed, sticking together, breaking apart, and assembling again in endless cycles. What formed from this turmoil were misshapen objects rotating and drifting through space, fragments of primordial disorder far removed from the calm symmetry we associate with planets. Many asteroids still preserve this appearance today. Missions like NASA's OSIRIS-REx to Bennu and JAXA's Hayabusa 2 to Ryugu revealed bodies resembling jagged, uneven potatoes, angular and strewn with loose material. They remain like this because their gravity is simply too weak to draw themselves into balance. But as a body grows larger, gravity begins to assert itself. In small objects, material strength rules. Rock resists bending, ice holds its form. Yet once an object reaches a diameter of roughly 600 kilometers, its own weight overwhelms that internal rigidity. Mountains begin to sag, craters slump inward, and the overall shape slowly starts to even out. Planetary scientists refer to this as gravitational relaxation, a gradual reshaping driven by internal pressure. It is not a sudden event. Solid rock requires tens of millions of years under constant stress to behave like a fluid. NASA's Dawn mission, which explored Vesta and Ceres, provided a striking illustration of this transition. Vesta, measuring about 525 kilometers across, sits just below the critical limit. Its form remains irregular, scarred by impacts, and only partially relaxed. Ceres, much larger, at around 940 kilometers, has crossed that threshold. Its gravity has softened ridges and valleys alike, drawing it into an almost perfect sphere. This dividing line where gravity overpowers material strength marks the shift from asteroid to planet. Astronomers describe it as hydrostatic equilibrium, the state in which a body's self-gravity is sufficient to force it into a rounded shape. Below this point lie the fractured remnants of the early solar system. Above it, true worlds emerge. The underlying physics is straightforward yet deeply profound. Gravity pulls evenly from all directions toward the center of mass. Any bump or protrusion creates uneven pressure. Greater mass beneath it compresses and spreads outward, while neighboring regions resist. Over geological timescales, rock slowly flows. It is difficult to picture stone as something fluid, but under immense pressure, even the hardest materials behave that way. Deep inside Earth, the mantle composed of solid silicate rock creeps at rates of mere centimeters per year. Over billions of years, that is enough to reshape an entire planet. Bruce Bannard of NASA's Jet Propulsion Laboratory once put it simply, if a planet were made of rock candy, gravity would eventually turn it into a jawbreaker. Every high point collapses, every low point fills until the forces balance. Gravity does not sculpt by cutting or carving, it sculpts by waiting. Every mountain is a temporary act of resistance, every crater is a mark that time intends to erase. After eons of compression and partial melting, the outcome is always the same roundness. Even the moon carries this narrative. Early in its history, it endured relentless bombardment that left its surface rough and broken, yet deep within its interior remained molten. That molten interior allowed gravity to redistribute mass, gradually smoothing the moon into the sphere we recognize today. The circular outline visible from Earth is no accident. It is physics made visible. The same principles apply to icy worlds such as Europa, Enceladus, and Titan. Their surfaces may be solid, but inside mixtures of rock, ice, and salty water deform plastically under pressure. Over time, their own weight compels them towards spherical shapes. NASA's Cassini spacecraft measured Saturn's moon Enceladus and found its form astonishingly close to what hydrostatic equilibrium predicts: smooth, round, and balanced. Despite being only about 504 kilometers wide, beneath its icy shell lies a global ocean kept liquid by tidal flexing gravity, again this time generating heat. What is remarkable is how universal this rule proves to be. Whether a body is composed of iron, rock, or ice, the same principle applies. If its gravity is strong enough to overcome material strength, it becomes round. If it is not, it remains jagged, a surviving relic of the universe's earliest roughness. The European Space Agency describes this evolution as a softening of the cosmos with time. Sharp edges yield to the pull of mass as energy dissipates and equilibrium prevails. What begins in violent collision ends in quiet stability. Even when later impacts occur, as they inevitably do, the balance largely endures. Craters and scars may appear, but the underlying symmetry persists. Earth, Mars, and Mercury all bear ancient wounds, yet their overall shapes remain faithful to gravity's constant effort to restore equilibrium. In rare cases, we can observe the opposite situation almost directly. The near-Earth asteroid Eros, studied by a rendezvous mission, is an elongated, lumpy body about 34 kilometers long. Its gravity is extremely weak, roughly 0.0059 meters per second squared, about 1/1700th of Earth's. At that strength, rock behaves almost like steel. There is simply not enough weight to pull it into a smooth form. Increase the mass 100-fold, however, and the situation changes entirely. Planetary geologists often compare this to a pile of clay. Small clumps retain their shapes, but once the pile grows heavy enough, it slumps into a smooth mound. The physics is identical, only the scale differs. Within a forming planet, this process continues unseen. As mass accumulates, pressure rises and generates heat. Radioactive decay adds further warmth, softening the interior and allowing material to move. Layers separate according to density. Heavy metals sink toward the core, while lighter silicates rise toward the surface. This is known as differentiation, and it is one of the most crucial stages in planetary evolution. Differentiation does more than make planets round. It makes them complex. It gives rise to magnetic fields, distinct crusts, and geological activity. Earth's magnetic field, for instance, is produced by the motion of liquid iron in its outer core, a direct consequence of this early gravitational sorting. Without it, our planet would be cold, airless, and exposed to the full force of solar radiation. So when we say that gravity sculpts a planet, we are describing something far deeper than surface shape. Gravity organizes interiors. It arranges layers, drives tectonic motion, and governs orbits. Every contour in the solar system, from the curve of Earth's horizon to the symmetry of Saturn's moons, began as the same quiet dialogue between mass and motion. It was once said that the universe is under no obligation to conform to human notions of harmony. And yet, when we observe the roundness of a planet, we are witnessing harmony emerging from chaos, not because it must, but because it is allowed to. Recent images from the James Webb Space Telescope of young planetary systems such as HL Tauri reveal glowing disks of gas already breaking into rounded clumps, the earliest hints of this same process. Each luminous knot within those disks is a future world already being shaped by gravity long before it hardens into rock or ice. Gravity is not a force of destruction, it is a force of patience. It does not strike or rush. It waits through impacts, through cooling, through collapse, until matter settles into its most stable form. And when that happens, a planet is born not through sudden creation, but through surrender. The jagged becomes smooth. The fractured becomes whole. What began as scattered debris becomes a world. But if gravity can guide rock into balance, what happens when it works on matter, even softer on vast clouds of gas, or on light itself? Does it still seek symmetry, or does the universe reveal something entirely new? Part 13. When does a piece of stone cross the line and become a planet? At what point does a drifting fragment cease to be rubble and begin to qualify as a world? Somewhere between drifting dust and fully formed planets, gravity quietly establishes an invisible boundary, a moment where randomness yields and structure takes hold. In the infancy of the solar system, there were no planets at all, only a vast rotating disk of gas and solid material fragments smashing together at hundreds of kilometers per second. From that turbulence, tiny grains began to cling to one another through electrostatic forces, the same gentle attraction that makes dust stick to your skin. Over time, these clumps grew into what we call planetesimals, the embryonic forms of future worlds. Yet in the beginning, they were nothing more than misshapen rocks, jagged and uneven, endlessly tumbling around the newly ignited sunday. Computer simulations of early planetary formation show that during the first 10 million years, there were trillions of such objects, from pebble-sized grains to bodies as large as mountains. Each one competed for material colliding and merging in a slow and chaotic cosmic draw. Then a decisive change occurred when gravity asserted itself. As a growing body crossed a critical threshold of mass, roughly a few hundred billion kilograms, corresponding to a diameter of around 600 to 800 kilometers, something profound happened. Its gravitational pull became strong enough to overpower the inherent stiffness of rock. The surface began to yield under its own weight. Peaks slumped, craters softened, and gradually the object reshaped itself into a sphere. That moment marks the genuine birth of a planet. Not the appearance of an atmosphere, not the capture of moons, but the instant when gravity becomes strong enough to pull the body into balance with itself. Astronomers refer to this condition as hydrostatic equilibrium. It is the same principle that governs stars, droplets of water, and even the structure of living cells. Under this definition, a planet is a body that orbits the Sun, possesses enough mass for its own gravity to overcome rigid forces so that it becomes nearly round and has cleared most other debris from its orbital path. That roundness is not cosmetic. It is evidence of internal authority. Scientists often describe it as the moment a rock gains coherence through gravity. Once a body can reshape itself against its own resistance, it becomes something fundamentally different. It is no longer just a fragment, but a self-organizing system. This boundary is visible throughout our solar system. Ceres, with a diameter of about 940 kilometers, has reached equilibrium. Its gravity has smoothed its surface and allowed it to retain a thin layer of water ice. Vesta, smaller at just over 500 kilometers across, has not. It remains angular and scarred, a survivor from an era before worlds learned how to be round. The same pattern repeats farther out. Icy moons such as Europa, Enceladus and Titan are spherical, shaped by their own gravity and internal heat. Smaller objects in the Kuiper belt, like Arakoth, retain stretched or double-lobed forms, clear signs that gravity has not yet fully claimed them. Haumea offers a remarkable example. It is massive enough to reach equilibrium, yet it spins once every 3.9 hours. So rapidly that centrifugal force stretches it into an elongated shape. This reveals just how fine the boundary really is. Gravity works to make a body round. Rotation works to tear it apart. The line between asteroid and planet is not symbolic, it is mechanical. Rock has a characteristic yield strength of about 100 million pascals. For gravity to reshape it, the pressure inside the body must exceed that value. Once an object becomes heavy enough for the pressure at its core to cross that limit, the material begins to flow. In this sense, planets are born through surrender, when matter gives way to its own weight. Once gravity prevails, an entire sequence follows. Internal heating begins as gravitational energy is converted into heat during compression. Dense elements sink inward, lighter materials rise toward the surface. This process of differentiation creates the layered structure seen in every mature world: a core, a mantle, and a crust. On Earth, the iron core formed within the first 30 million years of the solar system. That dense heart drives the magnetic field, protects the atmosphere, and stabilizes conditions that allow life to exist. Without this gravitational sourcing, which only begins once a body becomes round, none of this would be possible. Even the gas giants obey the same principle. Long before they gathered their vast hydrogen atmospheres, their solid or icy cores had already reached equilibrium. Shape came first, atmosphere followed. The same rule applies beyond our own system. Observations of young planetary systems show spherical clumps forming within protoplanetary disks, clear signs that gravity has already overcome rigidity and that new worlds are emerging. From the smallest dwarf planet to the largest giant, the pattern is universal. Roundness is the unmistakable signature of gravity's success. Once a body achieves equilibrium, even violent impacts cannot completely undo it. The surface may be battered and scarred, but the interior remains balanced. It is remarkable that such a thin margin, only a few hundred kilometers in size, determines whether a body remains jagged forever or evolves into a planet. Nature draws its boundary between disorder and harmony, not through color or composition, but through shape. The close encounter with Pluto revealed this vividly. Smooth plains, towering mountains of nitrogen ice, and signs of internal warmth left no doubt about its physical nature. Whatever label it carries, it satisfies the fundamental criterion. It is round, internally balanced, and governed by gravity. Even smaller moons show this transformation unfolding. Mimas, orbiting Saturn, sits near the edge of equilibrium. Its slightly stretched form suggests it is almost there, gravity nearly strong enough but not quite in command. This transitional zone captivates scientists because it captures the instant when order emerges from chaos. It is the universe's quiet threshold between what was and what will be, between rubble and architecture, between something that merely exists and something that endures. We are built from stellar material, but it is gravity that organizes it. That organization begins at this subtle boundary where a rock finally becomes a planet. It is humbling to realize that roundness, something so easily overlooked, is actually a marker of strength, patience, and deep time. Every smooth curve in the night sky tells the same story. Gravity has erased sharp edges, resolved tension, and taught matter how to settle. Yet not every body crosses that line. Many remain just short of it, fragments of unrealized worlds, drifting between definitions, too small for balance, too large for simplicity. And so the question remains, if roundness defines a planet, what are the bodies that never quite achieved it? Are they remnants of unfinished worlds, or the earliest hints of something yet to be born? Part 14. Is roundness part of what makes a planet a planet? When the announcement came in 2006 that Pluto had lost its planetary status, it felt as though time briefly paused. Schoolchildren altered their drawings of the solar system, astronomers argued passionately in lecture halls, and a small distant world at the edge of sunlight suddenly became the focus of a global debate. How could an object so elegantly spherical, carved with mountains, glaciers, and a vast heart-shaped plain, be told it no longer belonged? To grasp the reason, we must step back and confront a question that seems simple but is anything but. What does it truly mean to be a planet? Throughout history, that answer has shifted alongside our understanding. To ancient observers, any wandering light in the sky was a planet, even the sun and the moon. As telescopes sharpened our vision, the meaning narrowed. Then, in August 2006, the International Astronomical Union chose to set a formal definition. Under this ruling, a planet must meet 3 criteria. It must orbit the Sunday. It must be massive enough for gravity to pull it into a nearly spherical form, a state known as hydrostatic equilibrium. And it must have cleared its orbital region of other objects. Pluto satisfied the first 2. It journeys around the Sun once every 248 Earth years and forms a near-perfect sphere, roughly 237.6 kilometers wide, wrapped in a fragile nitrogen atmosphere and coated in ice and rock. The difficulty lay with the third condition. Beyond Neptune stretches the Kuiper Belt, a vast realm where Pluto travels alongside thousands of icy bodies, ranging from small comet-like fragments to worlds comparable in size. One of these, Eris, is almost identical to Pluto, and when discovered in 2005, even appeared slightly more massive. Had Pluto remained a planet, Eris and many others would have followed. To address this, astronomers introduced the category dwarf planet. These are objects shaped into spheres by gravity but unable to dominate their orbital zones. Roundness it emerged was essential but not enough. This moment marked a shift in modern astronomy. When a spacecraft swept past Pluto in July 2015, the discussion flared anew. The images were astonishing. Vast nitrogen, ice glaciers, mountains towering higher than the Rockies, and an atmosphere glowing blue as sunlight scattered through it. Pluto appeared active and intricate, everything we instinctively associate with planets. Some argued that if an object behaves like a planet, then it should be considered one. Others maintain that classification depends on gravitational authority. Pluto has not cleared its orbit. It is one member of a larger family, and that, they said, is not the role of a planet. This disagreement reveals something deeper about how we describe the universe. Nature does not draw boundaries, we impose them. The cosmos follows physical laws alone. A body becomes round when its own gravity overcomes internal rigidity. It clears its orbit when its mass outweighs everything nearby. Roundness is pure physics. Orbit clearing is about circumstance. And Pluto's circumstance is remarkable. Sitting nearly 6 billion kilometers from the Sun, it moves at a gentle 4.7 kilometers per second, far slower than Earth's rapid pace. Its orbit tilts 17 degrees from the plane of the solar system and stretches into an ellipse that sometimes carries it closer to the Sun than Neptune. Because of this, Pluto and Neptune engage in a delicate gravitational dance locked in a 3-to-2 resonance. For every 3 orbits Neptune completes, Pluto finishes 2. This precise rhythm prevents collision, a cosmic choreography of stability. Yet it also ensures Pluto can never rule its neighborhood. To clear an orbit, a planet must consume, expel, or scatter smaller bodies. Earth has done this, leaving a largely empty path. Jupiter has as well, though its gravity corrals asteroids into stable Trojan regions. Pluto, by contrast, shares its route with countless icy remnants left over from the birth of the solar system. Its shape meets the second rule, but the third remains unmet. By the standards of classification, that is decisive. Scientifically, however, Pluto is anything but trivial. The flyby revealed active glaciers, icy volcanoes, and a hazy atmosphere extending 200 kilometers above the surface. These are not features of a lifeless stone. They speak of internal warmth, chemistry, and geological vitality. Further analysis uncovered Sputnik Planitia, a vast frozen basin shaped like a heart filled with nitrogen ice circulating in slow convection currents. Pluto's heart truly pulses its surface, reshaped over millions of years as heat gently rises and fades. Even more surprising observations suggest its surface hosts complex organic molecules formed when ultraviolet light breaks apart methane. These compounds tint Pluto red and hint at chemical processes that echo those on the early Earth. So when we ask whether roundness defines a planet, the answer is both yes and no. Yes, because roundness signals the triumph of gravity. No, because it cannot capture the full character of a world. Categories shift just as they have before, and perhaps the meaning of planet will shift again. Roundness tells us a world has found internal balance, that gravity has smoothed away chaos. Clearing an orbit tells us about influence, about command within a system. Both reflect power, expressed differently. Pluto embodies this tension. It is small, yet astonishingly complex, remote, yet alive. Its shape shows it stands complete in itself. Its orbit shows it belongs to a community. Beyond Pluto, telescopes are revealing even more distant objects, some hovering on the edge of roundness, balanced between rubble and worldhood. Astronomers continue to search for a massive unseen planet far beyond Neptune, a giant that could once again reshape our understanding of the solar system. Until then, the question lingers. Is a planet defined by dominance or by dignity, by motion or by inner harmony? Roundness may not decide fate, but it declares that gravity has prevailed, that a world has settled into itself. And somewhere beyond Pluto, perhaps even now, another icy body is slowly gaining mass, quietly becoming smooth, waiting in silence to be noticed. Part 15. Why does the Sun hold its gases in such a flawless sphere? When you observe the Sun through a telescope fitted with the correct filters, you are not seeing a solid surface. You are witnessing a storm, a vast seething tempest of charged particles, tangled magnetic fields, and radiant light so powerful it could obliterate anything familiar to us, and yet despite this violence it is held together in an almost perfect symmetry. How can something so energetic, so chaotic, remain so round, so calm in appearance, so exquisitely balanced? At the core of the answer lies gravity, the same quiet but persistent force that shapes droplets of water, planets, and entire galaxies. The sun may resemble a blazing ball of fire, but in truth it is an enormous sphere of plasma, a form of matter in which atoms have lost their electrons. This vast sea of ions and electrons flows more like a liquid than a gas, endlessly shifting under the influence of heat and magnetism. Even with all this internal motion, the sun remains astonishingly round. Observations from NASA's Solar Dynamics Observatory, operating since 2010, revealed that the difference between the sun's polar and equatorial diameter is less than 10 kilometers. That is vanishingly small when set against a total diameter of 1.39 million kilometers. In geometric terms, the sun is more spherical than a spinning basketball, despite rotating once every 27 days at its equator. This remarkable stability comes from a finely tuned balance known as hydrostatic equilibrium. Gravity is always pulling inward, striving to compress the sun toward its center, while the pressure generated by nuclear fusion pushes outward, resisting that collapse. These opposing forces meet in near-perfect balance, preserving the sun's spherical form. At the core, temperatures soar to around 15 million degrees Celsius. Under such conditions, hydrogen nuclei fuse to form helium, releasing staggering amounts of energy. As described by Einstein's famous relation between mass and energy, a small fraction of mass is converted directly into energy. That energy becomes the light and heat that reach Earth after an 8-minute journey across nearly 150 million kilometers of space. The pressure produced by this fusion is immense, roughly 240 billion times the pressure of Earth's atmosphere. Gravity, however, is equally relentless. Without this balance, the sun would either collapse into a far denser object or tear itself apart in a catastrophic explosion. This equilibrium is what gives the sun and all stars their spherical nature. Where gas becomes too dense, gravity pulls it inward. Where it thins, pressure forces it outward. Over billions of years, this constant feedback smooths away irregularities, leaving a shape as close to perfection as the laws of physics permit. As one solar physicist once explained, the sun behaves like a self-regulating furnace. If the core grows too hot, fusion slows. If it cools, fusion accelerates. Gravity and pressure continually restore balance. This self-correction keeps the sun stable over astronomical timescales. For about 4.6 billion years, it has remained in this state, shining steadily, its near-perfect sphere maintained, while plasma roils beneath the surface. Yet beneath that serene appearance lies extraordinary motion. The outer layers churn through convection, where hot plasma rises, cools, and sinks again. Each convection cell can span the size of Texas, shifting constantly and creating the shimmering granulation patterns seen in high-resolution solar images. Even amid this turbulence, the overall symmetry endures. Magnetic fields twist and emerge, giving rise to sunspots, flares, and immense eruptions of charged matter. Still, the sun's shape barely alters. Gravity always outweighs the chaos. Measurements from solar observatories have shown that the sun's slight flattening due to rotation is almost negligible. Despite differential rotation, with the equator spinning faster than the poles, its deviation from a perfect sphere is less than 1/1000%. This is one of the most extraordinary facts in astronomy. The most violent object in our solar system is also one of the most geometrically precise. On microscopic scales, every particle inside the sun is in constant motion, colliding, fusing, and scattering photons outward. Trillions of interactions occur every second. Yet, when averaged across such vast numbers, they produce near-perfect symmetry. Physicists call this statistical equilibrium order, emerging naturally from randomness. It is deeply striking that chaos, when governed by fundamental laws and extended over immense scales, becomes order. The sun's roundness is a visible signature of that principle, proof that even the most turbulent systems find balance given enough time and gravity. Data from NASA's Parker Solar Probe, now flying closer to the sun than any spacecraft before it, show that the corona, the outer atmosphere, reaches temperatures exceeding 1 million degrees Celsius. Even this superheated plasma remains gravitationally bound, flowing outward as the solar wind, but never fully escaping the sun's influence. That gravitational reach extends far beyond what we can see, forming the heliosphere, an invisible bubble stretching more than 18 billion kilometers, enveloping all the planets and shielding them from interstellar radiation. In that sense, the sun's true sphere is far larger than its visible surface. When the James Webb Space Telescope studies distant stars, it reveals the same pattern repeated across the cosmos. From nearby red dwarfs to massive blue giants in distant galaxies, stars naturally assume spherical forms once gravity and pressure reach equilibrium. The sun is not exceptional. It is simply the closest example of a universal rule. That roundness, however, is not eternal. In about 5 billion years, when the sun exhausts its hydrogen fuel, equilibrium will fail. Gravity will compress the core while the outer layers expand into a red giant. The shape will swell and distort, then collapse once more as gravity reasserts itself. The sun will cast off its outer layers, leaving behind a white dwarf, about the size of Earth, still round, still balanced, but faint and cooling. Even in its final state, the geometry of stability persists. The cosmos is filled beyond measure with elegant truths and intricate relationships with the extraordinary machinery of nature. The sun's spherical form is one such truth, a balance so exact that it allows life to exist 150 million kilometers away, warmed but not destroyed. Every sunrise you have ever witnessed is a consequence of that equilibrium. Every photon that reaches your skin began its journey in the sun's dense, balanced core, born in fusion, wandering for hundreds of thousands of years through layers of plasma before escaping into space. The light arriving on Earth today may have started its journey before humanity existed at all. So when you watch the sun dip below the horizon, remember this. Even in all its fire and fury, it preserves its shape with mathematical precision, a sphere carved by invisible forces that have remained steady for billions of years. And yet, the sun's shape is not only a story of balance, it is also a clue to motion, to the interplay of rotation, pressure, and magnetism that sculpts the universe itself. What happens when a star spins too rapidly for gravity to restrain it? What new forms appear when equilibrium begins to bend? Part 16. Imagine Saturn spinning so rapidly that it can no longer remain round. If you were hovering just above the pale golden clouds and watching the planet turn, you would witness one of the most striking paradoxes in our solar system. Here is a world so enormous it could contain around 760 Earths within its vast interior, and yet it spins with astonishing speed, second only to Jupiter. Saturn completes a full rotation in just 10 hours and 33 minutes. For a planet more than 120,000 kilometers across, that speed borders on the extraordinary. At such a pace, gravity is pushed to its limits. By right, Saturn ought to be spherical. Gravity insists on it. But rotation has other ideas. As the planet spins, it is pulled outward, flattening at the poles and swelling around the equator. What emerges is not a perfect sphere, but an oblate spheroid, a graceful compromise between two competing forces, gravity pulling inward and rotation flinging matter outward. This distortion is so pronounced that it can be seen even from Earth. Saturn's equatorial diameter measures about 120,536 kilometers, while its polar diameter is only 108,728 kilometers. That is a difference of nearly 12,000 kilometers, close to 10% flattening, one of the most extreme examples anywhere in the solar system. To picture it more intuitively, if Earth were scaled up to the size of a basketball, Saturn would look as though its poles had been pressed inward by almost a full centimeter. Precise measurements from the Cassini spacecraft, which orbited Saturn between 2004 and 2017, revealed that the poles sit thousands of kilometers closer to the core than the equator. The planet is quite literally stretched by its own spin. This is not merely a matter of shape, it is physics made visible. As Saturn rotates, material near the equator experiences a strong centrifugal effect that pushes outward, countering gravity's inward pull. Near the poles, that outward force is weaker because the rotational speed there is lower. The consequence is a gentle squashing, creating a broad, bulging waste of gas and atmosphere. Saturn appears sculpted by motion itself, a world whose elegance arises from the balance between pressure, rotation, and light. That balance is what gives the planet its remarkable beauty. Despite spinning with such ferocity, Saturn does not fly apart. Its gravity, a little stronger than Earth's, at about 1.07 times our own, is sufficient to hold every atom of hydrogen and helium together, even as centrifugal forces try to hurl them into space. Yet the strain is visible in the atmosphere. Bands of powerful winds, immense storms, and rolling waves encircle the planet in soft golden ribbons. Cassini measured wind speeds near Saturn's equator, reaching up to 1,800 kilometers per hour, almost 5 times faster than the most violent hurricanes ever recorded on Earth. These winds race endlessly around the planet, driven by rotation itself, an unceasing atmospheric dance in which the gas is never truly at rest. And still amid all this apparent chaos, Saturn's overall structure remains astonishingly stable. Far beneath the clouds lies a vast ocean of molecular hydrogen, gradually compressed by immense pressure until it becomes metallic hydrogen. Near the core, pressures exceed 3 million times that of Earth's atmosphere. In this extreme environment, matter behaves in unfamiliar ways. Electrons move freely, forming an electrically conductive layer that generates Saturn's magnetic field. Curiously, that magnetic field is almost perfectly aligned with the planet's axis of rotation, a detail that continues to puzzle scientists since classical dynamo theory predicts at least a slight tilt. It hints that we are glimpsing something fundamental about how giant planets organize their interiors. Now consider what would happen if Saturn spun even faster. Beyond a certain critical speed, the centrifugal force at the equator would begin to rival gravity itself. The planet would flatten further, and the outer layers of gas could start to drift away in a process known as rotational instability. This is the same basic physics seen in rapidly spinning stars that shed material to form surrounding rings or disks. In that sense, Saturn's famous rings may be a visible sign of this delicate balance. Some scientists propose that the rings formed when an ancient moon, perhaps similar in size to Mimas, wandered too close and was torn apart by tidal forces. Others suggest that some of the material may have come directly from Saturn, expelled during periods of intense rotational or tidal stress. Cassini's final plunge through the rings in 2017 offered crucial clues. The spacecraft detected billions of icy particles falling into Saturn's atmosphere every second, more than 10 tons each second, dissolving silently into the clouds. This tells us the rings are temporary. Over the next 100 million years, they may vanish entirely, reclaimed by the planet's gravity. Even in their impermanence, the rings reveal that rotation and gravity are never truly at rest. They are always in negotiation. Saturn spins fast enough to distort its shape, but not fast enough to tear itself apart. That same rapid rotation also influences the planet's interior. Measurements of Saturn's gravitational field show that its internal layers, from gas to liquid metal, rotate at slightly different speeds. This differential motion gives rise to jet streams and atmospheric bands that slide past one another across different latitudes, reminiscent of Jupiter, though more restrained. And then there is the hexagon, one of Saturn's most intriguing features. First observed by Voyager 1" 1981 and later examined in detail by Cassini, this vast six-sided pattern circles the planet's north pole. It spans more than 30,000 kilometers, large enough to contain 4 Earths, and it rotates in step with the surrounding atmosphere. Scientists think it may be a standing wave formed by the interaction of fast-moving air currents at different latitudes, yet its remarkable stability over decades remains unexplained. Even here within turbulent motion geometry seems to assert itself. Another clue comes from Titan, Saturn's largest moon. When the Huygens probe descended through Titan's thick atmosphere in 2005, it discovered that the atmosphere rotates slightly faster than the moon's surface, a phenomenon known as superrotation. This may be one way angular momentum from Saturn's rapid spin is subtly shared with its moons and their atmospheres, a kind of cosmic handshake spanning millions of kilometers. All of this reveals just how profoundly rotation shapes the worlds around us. Saturn's spin governs not only its form, but its weather, its rings, and even the behavior of its moons. Without that speed, the planet might lose its flattened poles, its banded clouds, and perhaps its iconic rings as well. Yet this interplay between rotation and gravity is not unique to Saturn. It is universal. Every planet, every star, and every galaxy must settle into its own balance between these forces. As one astrophysicist once observed, every round object in space is the outcome of an ancient argument between spinning and falling. There is something reassuring in that thought. Even a world as dynamic and extreme as Saturn obeys simple physical laws, their consequences unfolding on a grand visible scale. The faster it spins, the more it stretches. The more it stretches, the more gravity pulls it back. This endless exchange writes Saturn's story one rotation at a time, and as the planet continues to turn silently and endlessly, it reminds us that even speed has limits, and even balance carries tension. Somewhere between spinning and braking, between gravity's pull and motion's defiance, lies the narrow boundary where worlds are born. And then we might ask, what happens when matter refuses to remain bound at all, when spin truly dominates and even light begins to curve around it? Far beyond Saturn, that is precisely what we find. Part 17. Why do Saturn's rings never gather themselves into a planet? If gravity's instinct is to sculpt worlds into spheres, why does this vast structure remain a flat, luminous disk? Why have uncountable fragments of ice, some no bigger than dust, others rivaling mountains, failed to unite into a moon? The answer lies in a subtle contest between gravity and motion, a balance so precise that creation is held permanently at bay. At first sight, the rings appear fragile, almost delicate, but that impression is misleading. They extend more than 282,000 kilometers outward from Saturn, yet their thickness is astonishingly small, typically only 10 to 30 meters. If Saturn were reduced to the size of a basketball, the rings would be thinner than a single sheet of paper. And within that impossibly thin plane exists one of the most intricate systems we have ever observed. The Cassini spacecraft, which explored Saturn for 13 years, revealed that the rings are composed of billions of particles of ice and rock, each following its own path. These fragments do not cling together, not because they lack the ability, but because the laws of motion deny them the chance. The reason is orbital mechanics, the same framework that governs moons, planets, and galaxies alike. Every object circling a planet moves at a speed that precisely balances gravitational attraction and outward motion. Within Saturn's rings, particles closer in complete an orbit in roughly 6 hours, while those farther out may take 14. This difference in speed, known as Keplerian shear, continually pulls neighboring particles apart. When two icy pieces drift close, they collide, gently trade energy, and move on. The variation in orbital speed ensures they never remain together long enough to grow. Cassini witnessed this directly. In 2017, as the spacecraft passed through the gap between Saturn and its innermost ring, it detected streams of fine particles moving independently like snowflakes suspended in orbit. Each fragment traced its own flawless trajectory together, creating the illusion of solidity. The rings also reside within a perilous zone called the Roche limit, the region where a planet's tidal forces prevent moons from forming. For Saturn, this boundary lies about 147,000 kilometers from its center. Any material inside this distance is stretched by gravity so strongly that anything attempting to merge is torn apart. In this way, Saturn's rings exist because of gravity and remain divided because of it. The same force that builds planets forbids their birth here. Data from the Jet Propulsion Laboratory shows that the ring particles are between 95 and 99% pure water ice, mixed with traces of silicate rock and organic compounds. Many are thought to be remnants of a moon that was destroyed either by collision or by tidal forces millions of years ago. Cassini also measured ring rain materials slowly falling into Saturn, suggesting the rings may be young on a cosmic scale, perhaps only 100 million years old. That means when dinosaurs walked the Earth, Saturn's rings may not have looked as they do now. This finding overturned decades of assumption that the rings were ancient leftovers from the birth of the solar system. Instead, the data shows that ring material is steadily lost to Saturn's gravity. The rings may be temporary, a fleeting chapter in the planet's long story. They are not eternal. They are structures in transition. Particle by particle, the rings may be disappearing into the world they orbit as gravity gradually reclaims what it once held apart. Yet before that happens, the rings continue their quiet dance governed by precision and physics. Within the rings, small moonlets only a few kilometers across do occasionally appear. Cassini observed several, including Pan-Daphnis and Atlas, embedded within gaps. These tiny worlds shepherd nearby particles, sending waves and ripples through the rings with their gravity. They act like cosmic conductors, maintaining rhythm and order, shaping edges and clearing paths, preserving the ring's graceful symmetry. Even these shepherd moons cannot grow beyond a limit. Inside the Roche region, any increase in mass only intensifies tidal stress. Saturn's gravity would tear them apart once more. The system regulates itself, locked forever in balance. This interplay of rotation, gravity, and distance is what makes Saturn's rings such a scientific marvel. They are not solid and they are not static. They are fluid, ever-changing expressions of motion, showing us that stability in the universe often comes not from stillness, but from perfectly repeated movement. The Cassini imaging team described the rings as a laboratory of orbital dynamics. Every ripple and every bright band records a gravitational interaction. Narrow gaps such as the Cassini division or the Encke gap mark regions where moons or resonances have swept material away. The Cassini division, the broad dark space between the A and B rings, aligns with a 2-to-1 orbital resonance with Saturn's moon Mimas. For every orbit, Mimas completes particles there, circle Saturn twice. Its repeated gravitational pull disrupts those paths and keeps the gap clear. Every curve and shimmer in the rings tells a story of timing and motion. What appears through a telescope as beauty is in truth mathematics made visible, gravity writing on ice. Light itself behaves differently here. Sunlight scatters off countless icy surfaces, creating the illusion of a solid sheet. Yet when Cassini viewed the rings in silhouette, it revealed their true nature, vast empty spaces where nothing dominates more than matter. The rings exist in a halfway state, neither solid nor vapor. They are what happens when gravity nearly creates something new, but spin holds it apart. Each particle follows its own path, yet together they form a coherent whole, like a symphony frozen in motion. The James Webb Space Telescope has begun observing the rings in infrared light, uncovering temperature differences across the bands. Inner rings are warmer, absorbing and re-radiating more sunlight, while the outer rings are cooler and more diffuse. Even here, energy obeys balance. So why do Saturn's rings refuse to become a planet? Because they already occupy a perfect equilibrium. Each orbit is exact, each motion predictable. Any attempt to merge would disrupt the harmony that sustains them. They are not failed planets. They are motion made visible. When Cassini ended its mission in September 2017, plunging into Saturn's atmosphere, it passed through the gap between planet and rings, a region never explored before. There it detected dust plasma and a faint electric current linking the rings to Saturn's upper atmosphere, proof that even in separation, they remain connected. As the spacecraft sent its final signal before vaporizing, it followed the same fate the rings themselves may one day face, falling inwards, spinning, yielding to gravity. Saturn reclaimed its explorer, just as it will eventually reclaim its rings. Until that day, Saturn's shining halo continues to teach us that perfection does not always mean unity. Sometimes it lies in harmony through motion. And beyond that, beauty waits a deeper question. If rings can remain suspended for millions of years, might other disks far larger and colder be doing the same across the universe, quietly preparing to give birth to stars or even galaxies? Part 18. Imagine peering through a telescope millions of years from now and discovering Saturn without its familiar splendor. No luminous bands, no shining crown, only a quiet, pale yellow world suspended in darkness. For much of human history, those rings felt timeless, as though they belonged to Saturn forever. Yet modern astronomy tells a different and far more delicate story. Those brilliant structures are fleeting. The mystery is no longer whether they will vanish, but when. Measurements gathered by NASA reveal that Saturn is slowly losing its rings, in a process so gentle it is almost poetic. Scientists call it ring grain. Every second, countless icy grains drift inward, guided by gravity, and swept along invisible magnetic pathways, falling into the planet's upper atmosphere. In the final phase of its mission in 2017, the Cassini spacecraft slipped through the narrow gap between Saturn and its innermost ring. There it measured this quiet downfall directly. What emerged was astonishing. More than 10 tons of material descend onto Saturn, each second comparable to an entire Olympic swimming pool of icy dust disappearing every single hour. If this pace persists, the rings could be gone within 100 to 300 million years, an instant on the scale of the universe. More surprising still, evidence from Voyager and observatories on Earth suggests the rings themselves may be only 10 to 100 million years old. They are newcomers, younger than the dinosaurs that once roamed our own planet. For something so majestic, their existence is painfully brief, one chapter of cosmic beauty destined to be erased. To understand how this erasure unfolds, we must look to forces we cannot see. Saturn's magnetic field stretches far into space, rotating with the planet roughly once every 10 hours. The icy particles of the rings interact constantly with this field. Bathed in sunlight and plasma from Saturn's atmosphere, they become electrically charged. At that moment, gravity is no longer the only influence upon them. Magnetic forces take hold, guiding the grains along field lines, drawing them down toward the poles, where they break apart and dissolve into the atmosphere. At NASA's Jet Propulsion Laboratory, this phenomenon is described as a vast celestial rainstorm of ice. As the particles fall, they trigger faint chemical reactions high above the clouds, producing subtle traces of hydrogen and oxygen ions that Cassini was able to detect. Saturn quite literally is consuming its own rings, quietly and continuously. The process is as graceful as it is unavoidable. The same gravity that once shaped those immaculate rings is now reclaiming them. Over immense spans of time, drag from the upper atmosphere and forces driven by sunlight slow the particles further, drawing them ever inward. One of the scientists involved in confirming this process remarked that we are extraordinarily fortunate to witness Saturn's rings at all. If they are temporary, then our moment in history coincides with a rare cosmic alignment. Among the thousands of planets discovered throughout the galaxy, none display a ring system quite like this. Other giants possess rings, but theirs are faint and dusty, little more than whispers of structure. Saturn's are vast, radiant, and composed largely of pristine water ice that reflects sunlight like polished glass. That very purity is also their weakness. Radiation from the sun and impacts from tiny meteoroids gradually damage and darken the ice. With each collision, the particles fracture and scatter. As material is lost and replenished in uneven measure, the once brilliant rings slowly dim, thinning until they finally fade away. Cassini's dust analyzer revealed yet another layer of complexity. The ring particles endure constant bombardment by meteoroids, each impact ejecting fresh debris into Saturn's gravitational grip. The system renews itself even as it destroys itself, locked in an endless cycle of gain and loss. So what truly erases the rings is not time alone. It is friction and magnetism, radiation and gravity all acting together in a delicate harmony. These unseen forces create one of the most exquisite balances we have ever observed in nature, and one that is destined to conclude. Yet the origin of the rings may be even more dramatic than their demise. In 2022, scientists re-examining data from Cassini's final flybys proposed that the rings were born from catastrophe. They suggest an ancient icy moon known as Chrysalis once orbited Saturn before tidal forces tore it apart. The debris from that destruction may have spread outward and flattened into the rings we admire today. This idea also helps explain Saturn's distinctive axial tilt, its pronounced lean relative to the Sunday. The loss of that moon would have altered Saturn's balance, granting it both its elegant tilt and its breathtaking rings. In this view, Saturn's beauty emerged from violence, and its fading marks the quiet resolution of that same event. Today, the James Webb Space Telescope is examining the rings in unprecedented detail, probing their infrared signatures to assess how pure the ice remains. If Webb detects significant darkening from accumulated dust, it will confirm that the rings are aging their brilliance, diminishing year by year. Even now, observatories on Earth can register subtle shifts in brightness. They are small and almost imperceptible, yet undeniably real. The story of Saturn's rings is not frozen in time. It is unfolding before us. It is humbling to realize that if humanity had appeared a few 100 million years earlier or later, these rings might never have been seen at all. We are made of the same cosmic material we observe, contemplating a momentary perfection formed from ice and dust. When the rings finally vanish, Saturn will remain a smooth and nearly perfect sphere stripped of its adornment. Without the rings, it will resemble Jupiter, vast and tranquil, its gravity unchanged and its path around the sun undisturbed. What will remain are memories preserved in data and images that inspired generations. Perhaps as the final fragments spiral inward, they will glow briefly from friction, creating a last faint veil of light as they fall. In that quiet farewell, Saturn will return to the form it held billions of years ago, complete and unadorned. The true beauty of the rings lies in their impermanence. They remind us that even in the immensity of space, not every wonder endures. Some exist just long enough to be witnessed, just long enough for a civilization like ours to look upward in awe. So when you observe Saturn through a telescope, its shining rings encircling the planet like a frozen halo, remember that you are seeing a fleeting moment that the universe itself will one day forget. And when those rings are gone, erased by the very gravity that brought them into being, Saturn will persist, balanced and serene. And it invites a deeper question. If such slow reclamation is happening here, might similar processes be unfolding elsewhere across the cosmos on scales so immense that entire galaxies could be shedding their luminous halos, dissolving gradually into quiet symmetry? Part 19. How did Earth's moon emerge from something as fleeting as a ring? Imagine for a moment that the quiet presence hanging above us each night was once a swirling band of incandescent debris, more akin to Saturn's rings than the familiar sphere we know. Before there was elegance in the night sky, there was destruction on a staggering scale. Around 4.5 billion years ago, shortly after our planet took shape, a single catastrophic event reshaped the destiny of Earth. A protoplanet roughly the size of Mars, now known to science as Theia, struck the young Earth at a velocity exceeding 15 kilometers per second. The energy released was almost inconceivable enough to liquefy both bodies and hurl enormous quantities of molten rock and vaporized metal into space. For a brief interval in cosmic history, Earth was encircled by a ring not composed of ice crystals but of glowing liquid stone. Simulations conducted by researchers at NASA suggest that this debris extended tens of thousands of kilometers outward, shining a fierce orange against the blackness of space. Some fragments quickly fell back to the planet while the rest spread into a flattened disk temporarily surrounding Earth like a fiery halo. With time, that incandescent ring began to change. Gravity, quiet and relentless, drew the material together, particle by particle, fragment by fragment. On the scale of planetary history, the transformation was astonishingly rapid, perhaps only a few thousand years. As the debris cooled, what had been molten gradually solidified, assembling into a single body. That body became the Moon, about 3,474 kilometers across, now circling Earth at an average distance of 384400 kilometers. Born in chaos, it was shaped into harmony by gravity. Evidence gathered from lunar missions and orbital observations supports this idea known as the giant impact hypothesis. The chemical makeup of lunar rocks, particularly their oxygen isotope ratios, is nearly indistinguishable from that of Earth's mantle. It is a subtle but powerful signature, revealing a shared origin. This remarkable similarity rules out the notion that the Moon was captured from elsewhere or formed independently. And yet puzzles remain. Early simulations suggested that much of the Moon should consist of material from Theia, but analyses of lunar samples show almost no unique chemical trace of that impactor. The implication is profound. The collision must have mixed Earth and Theia so completely that the Moon became an almost perfect blend, half Earth and half intruder, indistinguishable at the atomic level. One of the scientists who developed these models described the Moon as Earth's offspring, made of the same substance but forged in fire. It is difficult to picture, but the newborn Moon bore little resemblance to the serene object we see today. In its earliest state, its surface was a global ocean of magma hundreds of kilometers deep. As cooling progressed, denser minerals sank toward the interior, while lighter components rose, creating the Moon's first crust. The familiar scars we observe now, vast craters, basins, and dark volcanic plains, appeared much later, after billions of years of bombardment. Even before those features formed, however, the Moon was already influencing Earth's future in a fundamental way. Its gravitational pull stabilized Earth's axial tilt, preventing wild variations that could have led to extreme and unpredictable climates. Without the Moon, Earth's seasons might have been erratic, its tides feeble, and its rotation dramatically faster. The presence of the Moon helped make Earth a place where life could persist. All of this traces back to a single collision. Today, scientists can even recreate the motion of that ancient debris. Advanced computer simulations from research teams show molten fragments looping around Earth in luminous arcs, gradually coalescing into one dominant body. Smaller pieces either rained back down onto the planet or escaped into independent paths around the sunday. The entire process may have unfolded in just a few decades, an instant in planetary terms. Yet, in that instant, Earth gained its companion, a ring transformed into a world. There is something deeply striking about this, the way nature reuses the same physical laws. The same balance between motion and gravity that keeps Saturn's rings from collapsing once allowed Earth's ring to do exactly the opposite. Around Saturn, particles remained too dispersed and moved too quickly to merge. Around Earth, they were close enough and gravity was strong enough to draw them together. Scientists have described this transition with elegant simplicity. The Moon is what happens when a ring is allowed to fall inward. Even the Moon's rotation preserves the memory of its origin. In its early history, the Moon spun rapidly. Over time, Earth's gravity slowed that rotation and locked it into tidal synchronization, ensuring that one face always points toward us. That same interaction gradually slowed Earth's own spin, stretching our days from about 6 hours in the distant past to the 24 hours we experience now. The process continues today. Precise measurements using laser reflectors left on the lunar surface show that the Moon is still drifting away from Earth by about 3.8 centimeters each year. This slow retreat is part of a long gravitational exchange that began in fire and will one day settle into quiet equilibrium. Earth stabilizes the Moon and the Moon stabilizes Earth. Their motions are intertwined, sharing energy in a dance that started when the first droplets of molten rock cooled while circling our planet. More recent studies, including detailed isotopic analyses of samples returned from the Apollo missions, hint at an even more dramatic possibility. The Moon may have formed almost immediately after the impact, perhaps within hours rather than millennia. This idea is known as the synestia model, In this scenario, Earth and Theia briefly merged into a vast spinning structure of vaporized rock, something like a glowing, rotating donut, before contracting and separating. In that moment, Earth itself would have been a radiant vortex, its outer layers forming a transient disk from which the moon condensed, rather like a droplet, crystallizing from steam. It is a bold idea, but one that is gaining support, and it blurs the boundary between ring and world almost completely. Future observations may help sharpen this picture. By examining young planetary systems around distant stars, astronomers observe disks of gas and dust that resemble what Earth's debris disk might once have been. In those systems, we may be watching moons in the process of formation, witnessing the same mechanisms at work that shaped our own world billions of years ago. So when you next see the moon rise calm and luminous, it is worth remembering that it carries the imprint of extraordinary heat. Its smooth, tranquil face is the final state of an event, so violent it nearly tore our planet apart. Beneath its stillness, every atom holds the memory of the ring it once belonged to. Every world, after all, is a record of transformation. The moon's journey began in disorder and ended in balance. The same laws that sculpt planets, rings, and galaxies operate at every scale. In the end, anything that spins seeks equilibrium. Anything that scatters eventually takes form. And sometimes, a ring learns how to become a world. Yet one question remains, reaching beyond moons and rings and even planets themselves. If roundness and symmetry keep emerging throughout nature, might they be hinting at something deeper, a fundamental order woven into the fabric of space-time itself? Part 20. Why do droplets become flawless spheres when gravity is absent? Release a single drop of water inside the International Space Station and it does not fall. It does not spread across a surface, flatten, or burst apart. Instead, it drifts, calmly drawing itself inward until it becomes a luminous, perfectly rounded sphere. In microgravity, water loses any sense of direction. There is no up or down, no weight pressing it against anything solid. Each molecule pulls on its neighbours with equal strength from every direction, and from that perfect balance emerges one of nature's most elegant forms, the sphere. Astronauts aboard the ISS have repeated this demonstration many times. They release small amounts of coloured water into the still cabin air and watch as shimmering globes form, sometimes several centimetres wide. When light passes through them, the droplets behave like lenses, bending and refracting their surroundings. This is the same principle that shapes soap bubbles on Earth through surface tension. At the microscopic scale, every molecule on the surface of the liquid feels an inward pull from those around it. That inward force works to minimize surface area, creating the smallest possible boundary for a given volume, which is a sphere. In orbit, you can witness physics stripped to its essentials. With gravity removed, the laws of cohesion and energy efficiency reveal themselves clearly. These are the same principles that shape droplets, stars, and even planets. To understand why droplets are round, we can begin with a simple relationship. E equals gamma times A, where E represents surface energy, gamma is surface tension, and A is surface area. Nature always seeks the lowest possible energy state. To reduce E, a liquid reduces A, adopting the shape with the smallest surface area for its volume, the sphere. Every drop of water floating inside the ISS follows the same rule that governs Jupiter, the Sun, or any object held together by its own internal pull. The scale changes, but the physics remains the same. Things become even more intriguing when astronauts interact with these floating spheres. Touch one gently, and it trembles, almost as if it were alive. Send a puff of air toward it, and it begins to oscillate briefly, breaking its symmetry, before settling back into equilibrium. High-speed cameras on the station have captured these motions in extraordinary detail. Each oscillation mode, each subtle ripple across the surface, aligns precisely with mathematical predictions made more than a century ago. Those equations describe how surface tension restores a disturbed droplet to its spherical form. Even the smallest disturbance cannot disrupt that balance for long. Gravity may shape worlds, but in this tiny floating environment, surface tension plays the same role. Astronauts have also mixed colors within water droplets, recording how dye spreads in microgravity. On Earth, convection driven by heat causes fluids to rise and fall, naturally stirring liquids. In orbit, without up or down, molecules move only through diffusion. The result is a slower, quieter chemistry, revealing processes normally hidden by gravity. This becomes a laboratory where every movement matters. A floating sphere of water turns into a tool for understanding how stars ignite, how planets assemble, and how life itself might behave in low gravity. In 2015 experiments in the ISS Fluid Science Laboratory examined oscillating droplets using controlled vibrations. When energy was applied, the droplets briefly stretched into elongated shapes, sometimes resembling ellipsoids or dumbbells, yet they always returned to perfect roundness once the motion stopped. That return is more than visual elegance. It is physics demanding balance. The same principle keeps planets, spherical stars stable, and galaxies ordered. An astronaut scientist once remarked that when you play with water in space, you are observing the same mathematics that binds the cosmos together. Imagine enlarging one of those tiny droplets to the size of a planet. The forces would be renamed. Surface tension would become gravity. Molecular cohesion would become mass attraction. Yet the geometry would remain identical. Every point would pull equally toward the center, forming a sphere. This is why microgravity is often called the great equalizer. It removes the distraction of weight and reveals symmetry as the universe's native language. More recently, experiments aboard the ISS extended this idea by studying oil and water droplets spinning inside sealed chambers. As the droplets rotated, they flattened slightly at the poles, mirroring the way planets bulge at the equator due to rotation. It was a miniature version of a gas giant suspended in a laboratory. Poetic, yes, but also precise physics. Motion reshapes matter in the same way, whether the object is a droplet or a world. At the smallest scale, this research helps engineers understand how fuel behaves in spacecraft tanks where liquid propellants drift freely in weightlessness. At the largest scale, it explains how galaxies flatten into disks and how stars maintain internal balance. The more closely scientists observe these droplets, the clearer the connection becomes. The laws governing a few grams of water are the same laws governing billions of tons of plasma inside a star. The rules are consistent, elegant, and astonishingly universal. Through modern telescopes, astronomers now see similar spherical and near-spherical structures throughout the cosmos. Protoplanetary disks curling towards symmetry, nebulae glowing in delicate balance, young stars wrapped in near-perfect halos of dust and gas. The same story unfolds from micrometers to light years. Inside every sphere, whether a droplet or a planet, there is a dialogue between pressure and pull, between cohesion and freedom. Nature does not waste energy, and roundness is its solution to efficiency. So when astronauts chase shimmering globes of water inside the ISS, smiling as the droplets drift away, they are witnessing one of the most fundamental dances in physics, a small-scale echo of what gravity does to gas and dust, to stars and galaxies over billions of years. The tiny and the immense reflect one another. What happens within a few centimeters of floating water also happens across the universe. When a droplet finds its perfect shape, the laws of nature complete their work from the molecular to the galactic. Every curve, every surface, every rotation obeys a single, quiet rule: balance. And within that balance, inside a sphere of water suspended between nothing and everything, the entire story of the universe is written in miniature.